Hello there and welcome to Science for Sleep, where curiosity gets cozy and the universe slows down just enough for us to wander through it together. Tonight we're heading towards something so enormous, so violently bright, and so difficult to fully imagine that even astronomers sometimes describe it with a kind of exhausted disbelief. Our destination is a star called R136a1, currently considered the most massive star ever discovered. Not the biggest planet, not the largest black hole, a star. A single burning object in space so extreme that it almost sounds like a mistake in the data. Now, stars are already quite ridiculous when you think about them for more than a few seconds. Even our own sun, that warm glowing thing currently minding its business above Earth, contains more than 99% of all the mass in the solar system. You could fit more than 1 million Earths inside it, though admittedly that would create several logistical problems. The sun is so large that light itself, travelling at the fastest speed physically possible, still takes over 4 seconds just to cross its diameter. And yet, compared to R136a1, the sun begins to look strangely modest, respectable, sensible, like a quiet little neighbourhood bakery sitting beside an active volcano. Before we drift deeper into tonight's story though, I'd love to ask something fitting for an evening spent talking about giant stars. Where are you listening from tonight? Is it late where you are? Early morning? Perhaps rain is tapping gently against the windows, or maybe the room is completely still except for the sound of this voice and whatever thoughts followed you into the dark. And if you find these slow journeys through science relaxing or comforting after a long day, feel free to like the video and subscribe. It helps this calm little corner of the universe continue growing, which is reassuring because unlike R136a1, I promise the channel is not at immediate risk of exploding catastrophically. Now then, let's settle in. Because somewhere inside a neighbouring galaxy, wrapped in clouds of violent gas and crowded among thousands of younger stars, sits an object so luminous that it pushes against the limits of how large a star can even become. A cosmic furnace so intense that astronomers are still debating how nature managed to build it in the first place. And strangely enough, the story begins with a problem. For most of human history, stars seemed simple. Distant lights, fixed points, decorations scattered across the night sky. Ancient civilizations tracked them, navigated by them, worshipped them, and built entire mythologies around them. But no one truly understood what stars were. Not really. Even as telescopes improved, stars remained frustratingly unreachable. Planets showed disks and details. Jupiter had stripes. Saturn had rings. The moon revealed mountains and craters. But stars stayed stubbornly tiny. Bright points. Tiny holes punched into darkness. Then slowly, science began peeling away the mystery. Astronomers realized stars were suns, massive spheres of gas held together by gravity. They learned stars are born, age, swell, collapse, and die. Some quietly fade away. Others detonate with enough force to briefly outshine entire galaxies. And along the way, scientists noticed something curious. Stars seemed to follow rules. There appeared to be natural limits to how small and how large they could become. Tiny stars called red dwarfs could survive for trillions of years. Larger stars burned hotter and faster. The more massive the star, the shorter and more chaotic its life became. It's a little counterintuitive at first. Bigger stars do not live longer, they die faster. Imagine 2 candles. One burns with a calm, steady flame. The other is essentially a flamethrower having an emotional crisis. The second candle may contain more fuel, but it also consumes that fuel with astonishing recklessness. That is how giant stars behave. Our Sun, for example, is expected to live for around 10 billion years. It's currently middle-aged by stellar standards. Calm, stable, predictable, a responsible adult star. But stars much larger than the Sun live dramatically shorter lives. Some survive only a few million years before tearing themselves apart. And that brings us to one of the strangest facts about R136a1. This star is probably younger than some trees on Earth feel emotionally. Not literally, of course. Trees do not usually express opinions about stellar evolution, but in cosmic terms, R136a1 is astonishingly young, a newborn monster already burning through its lifespan at terrifying speed. Because the larger a star becomes, the more gravity squeezes its core. That pressure drives nuclear fusion faster and faster, until the star becomes unimaginably luminous. R136a1 releases millions of times more energy than the Sun. Every second, it pours radiation into space with such violence that the star is effectively trying to blow itself apart, and in many ways, it is succeeding. But we're getting ahead of ourselves. First, we should probably discuss the uncomfortable scale of this thing because human brains are not naturally equipped for stellar measurements. Evolution prepared us for finding berries, avoiding cliffs, and occasionally staring into refrigerators despite already knowing what's inside. It did not prepare us for objects containing hundreds of times the mass of the Sun. The Sun itself has a mass of about 2 octillion tons. Written numerically, that is a 2 followed by 30 zeros, which is generally the point where most people stop emotionally connecting to the number and simply nod politely. R136a1 is estimated to have once contained well over 300 solar masses when it first formed. Even now, after shedding enormous amounts of material through violent stellar winds, it likely remains somewhere around 170 to 200 times the mass of the Sun. That number is difficult to appreciate because stars are not solid. They are giant balls of plasma, heated to such incredible temperatures that atoms themselves are stripped apart. No surface to stand on, no mountains, no oceans, just pressure, radiation, gravity and fusion locked in a delicate cosmic argument. And despite all that mass, R136a1 may not actually be the physically largest star by diameter. That title belongs to swollen red supergiants like UY Scuti or Stephenson 2-18, stars so bloated they would engulf the orbit of Jupiter if placed inside our solar system. R136a1 is different. It is not merely huge, it is dense with energy. Compact compared to the puffed-up giants, hotter, brighter, more violent. Its surface temperature exceeds 50,000 degrees Celsius. The Sun's surface is around 5,500. At those temperatures, ordinary intuition breaks down very quickly. Matter behaves differently. Light behaves differently. Even the colour changes. Stars like the Sun glow yellow-white. Cooler stars appear red. But R136a1 burns with an intense blue light, the signature of extreme heat. If our Sun were replaced with R136a1, Earth would not merely become warmer. The planet would effectively cease to exist almost immediately in any recognizable form. Oceans, atmosphere, crust, chemistry, memory, history. Every trace of human civilization would be erased beneath radiation powerful enough to sterilize enormous regions of space. Which perhaps sounds slightly alarming for a sleep video, though there is some comfort in knowing R136a1 is safely located about 160,000 light-years away inside the Large Magellanic Cloud, a neighbouring dwarf galaxy orbiting the Milky Way. So, no immediate concerns there. Probably. Still, the existence of R136a1 forces astronomers to confront an interesting question. How large can a star actually become before physics refuses to cooperate? For a long time, scientists believed stars above roughly 150 solar masses should not exist. Radiation pressure from the forming star would become so intense that it would blow away the surrounding gas before additional material could fall inward. Essentially, the star would interrupt its own growth. Imagine trying to build a sandcastle while simultaneously operating a leaf blower directly at the sand. And yet, nature apparently ignored the memo. When astronomers observed the dense star cluster called R136 inside the Tarantula Nebula, they discovered objects so luminous and massive that the old theoretical limits suddenly looked uncertain. At first, scientists thought the observations might actually represent multiple stars blurred together. That would have been the safer explanation. Unfortunately for astrophysicists hoping for simplicity, improved observations kept pointing toward the same conclusion. Some of these stars really were that massive. Among them, R136a1 stood out as the largest known example. Even its name sounds oddly bureaucratic considering the sheer absurdity of the object itself. R136a1. Not exactly the title of a cosmic deity, more like a printer model that occasionally jams paper. Astronomy often works this way. The universe produces wonders beyond imagination, and scientists respond by assigning labels that sound like parking permits. But behind that dry catalogue name sits one of the most extreme objects humanity has ever identified, and perhaps the strangest part is this. R136a1 is probably not unique. That idea changes the emotional scale of the universe a little. Somewhere across the cosmos there may be countless giant stars forming, burning and dying beyond our ability to observe them clearly. Entire stellar populations briefly flashing into existence before vanishing in explosions so violent they forge heavy elements necessary for planets and eventually life. In a very literal sense, giant stars helped make you possible. The iron in your blood, the calcium in your bones, the oxygen you breathe, much of it originated inside stars. Earlier generations of stars lived and died long before the sun existed. Their explosions scattered heavier elements into space. Later clouds collapsed. New stars formed. Planets emerged. Chemistry grew more complicated. Eventually, somewhere on a small rocky world, a species evolved capable of lying awake at night wondering what stars are. There's something quietly comforting about that chain of events. Not because the universe was designed for us. It almost certainly was not. But because existence itself turns out to be deeply connected. The atoms inside your body were once part of ancient stellar furnaces. Every person listening tonight is carrying tiny remnants of exploded stars around with them all the time, which admittedly sounds dramatic but is also scientifically accurate. R136a1 represents that process pushed toward the absolute extreme. A star so massive that it may spend its entire existence balancing on the edge of destruction. Even now, powerful stellar winds are blasting material away from its surface at enormous speeds. The star is literally evaporating itself into space, and it does all this while sitting inside one of the most chaotic stellar nurseries nearby, surrounded by radiation, shock waves, and dense clouds of gas illuminated in eerie shades of pink and blue. Not exactly a peaceful neighbourhood. Astronomers studying regions like this often describe them as star factories, though the reality is less organised assembly line and more cosmic weather system mixed with controlled detonation. Gravity pulls gas inward. Radiation pushes outward. Shock waves trigger new collapses. Massive stars ignite and begin disrupting the very clouds that created them. Everything influences everything else. And somewhere within that turbulence, R136a1 emerged. A star so luminous that if it were placed where the sun currently sits, it would dominate Earth's sky beyond comprehension. Daylight would become meaningless. The atmosphere itself would likely ionize beneath the radiation. Shadows might disappear entirely beneath overwhelming brightness. Of course, humanity would not survive long enough to appreciate the view. Still, imagining these scales helps reveal something important about the universe. Nature does not always favour moderation. Sometimes gravity builds carefully balanced systems like our solar system. Other times it creates giant unstable stars burning themselves apart with astonishing extravagance. R136a1 belongs firmly in the second category. And oddly enough, its very existence may offer clues about the early universe itself. Because long ago, shortly after the Big Bang, conditions may have favoured the formation of stars far larger than most we see today. Ancient monster stars, short-lived giants that shape the chemistry of the young cosmos. In some ways, R136a1 may be a surviving glimpse of that older universe, a modern echo of a more violent cosmic age. Long before astronomers understood exactly what R136a1 was, they already knew something unusual was happening inside the Tarantula Nebula. Even from enormous distances away, the region looked excessive, too bright, too energetic, like part of the universe had accidentally turned the settings too high and then quietly walked away, pretending nothing had happened. The Tarantula Nebula itself sits inside the Large Magellanic Cloud, a nearby dwarf galaxy, orbiting the Milky Way at roughly 160,000 light-years from Earth. Nearby, of course, is a relative term in astronomy. If you tried driving there at highway speeds without stopping for fuel, food, or emotional support, you would arrive sometime after the complete extinction of humanity, continental drift, and probably several future species of crab. Still, by galactic standards, the Large Magellanic Cloud is close enough for astronomers to study in remarkable detail. On clear southern nights, it appears faintly visible to the naked eye as a hazy detached patch of light. Ancient cultures noticed it long before telescopes existed. Sailors navigating southern oceans used it as a reference point. Eventually, European astronomers catalogued it formally, although, as usual, the universe had been operating perfectly well without waiting for official paperwork. Inside this neighbouring galaxy lies the Tarantula Nebula, also known as 30 Doradus, an enormous region of gas, dust, radiation and furious star formation. Calling it a nebula sometimes creates the wrong mental image. The word sounds soft, gentle, cloud-like, something drifting peacefully through space. The reality is considerably more violent. The Tarantula Nebula spans hundreds of light-years and contains enough material to form millions of stars. Massive young suns blast radiation outward in all directions. Shock waves ripple through gas clouds. Stellar winds collide at terrifying speeds. Entire regions glow because ultraviolet radiation strips electrons from atoms, turning the nebula into an enormous luminous storm. If Earth somehow existed inside the denser central regions of the Tarantula Nebula, the night sky would not really have nights anymore. Massive stars would dominate the heavens continuously. Radiation levels would be catastrophic. The surrounding gas would glow faintly even without moonlight. It would feel less like looking into space and more like standing inside the engine room of the universe itself. And buried deep within that chaos sits a dense star cluster called R136. At first glance, R136 didn't seem especially strange. Astronomers had already discovered many star clusters by the mid-20th century. The Milky Way alone contains thousands of them. Some are ancient globular clusters filled with elderly stars orbiting the galaxy like forgotten cosmic retirement communities. Others are younger open clusters where stars form together from collapsing clouds of gas. R136 appeared to be one more densely packed stellar nursery. But then telescopes improved, and suddenly the numbers stopped making sense. Even in the early observations, astronomers noticed the central region of R136 was unbelievably bright. Not bright in the ordinary astronomical sense, where everything already involves terrifying quantities of energy. This was excessive even by stellar standards. Initially, researchers assumed the explanation must be simple. The centre of the cluster probably contained many stars packed tightly together, too close for telescopes to separate clearly. Their combined light blended into what looked like a single object. That interpretation felt comfortable, safe, predictable. Astronomy often works this way. When observations appear impossible, scientists first suspect the instruments, the data, or their interpretation before rewriting the laws of stellar physics. And usually that caution is justified. Nature tends to follow rules, even if humans misunderstand them occasionally. So for a while, R136 remained categorized as a compact cluster core rather than a single giant star. Then came sharper observations. By the 1970s and 1980s, Advances in telescope technology allowed astronomers to resolve increasingly fine details inside distant star-forming regions. Observatories in Chile and elsewhere began studying the Tarantula Nebula more carefully. Researchers used spectroscopy, analysing the light emitted from stars to determine temperature, composition, and motion. This is one of the quietly astonishing achievements of astronomy. Humans cannot physically travel to stars, yet by studying light alone, scientists can determine what distant suns are made of, how fast they rotate, how hot they burn, and even whether they are moving toward or away from us. It's rather like identifying a campfire from thousands of kilometers away, while also determining what kind of wood is burning and whether someone added too much lighter fluid. The more astronomers examined R136, the stranger it became. The cluster's central stars appeared extraordinarily hot and luminous. Their spectra suggested the presence of extremely massive young stars known as Wolf-Rayet stars, objects already famous for their violent stellar winds and unstable behaviour. These stars eject enormous quantities of matter into space, at speeds reaching millions of kilometres per hour. Even among Wolf-Rayet stars, though, something about R136 stood out. The luminosity estimates were alarming. Luminosity is essentially a measurement of total energy output. The Sun produces a tremendous amount of energy every second, roughly 386 billion megawatts, enough to power human civilization many times over, assuming civilization could somehow plug directly into a star without immediately vaporizing. R136's central objects appeared millions of times brighter than the Sun. Now, brightness alone can be misleading. A group of stars packed together can mimic the luminosity of one larger object. But as the observations improved, astronomers realized the central light source was resolving into several individual stars, each unbelievably powerful on its own. And among them, one object emerged as especially extreme. R136a1. The name itself reflects the structure of the catalogue system. R136 refers to the cluster region. The A marks a subsection. The one identifies the specific star. It sounds technical because astronomers tend to reserve emotional reactions for conferences and quietly panicked research papers rather than object names. But behind that calm designation sat an increasingly uncomfortable discovery. The mass estimates for R136a1 began climbing higher and higher. 100 solar masses, 150 solar masses, 200. Eventually, some calculation suggested the star may have formed with well over 300 times the mass of the Sun. At that point, astronomers faced a serious problem. Theoretical models said stars that massive should not exist, not comfortably anyway. To understand why this was troubling, we need to talk briefly about how stars form. Stars begin inside cold molecular clouds, where gravity pulls gas inward. As material collapses, pressure and temperature increase until nuclear fusion ignites in the core. Once fusion begins, the star starts generating outward radiation pressure. That radiation matters. A forming star doesn't passively collect gas forever. Its own energy begins pushing surrounding material away. The larger and brighter the star becomes, the harder it is for gravity to continue feeding it additional mass. Eventually, a limit should appear. Radiation pressure becomes so intense that further growth effectively stops. For decades, astronomers believed that limit sat somewhere around 100 to 150 solar masses. Then R136a1 arrived, and behaved like physics hadn't received the update. At first, many scientists resisted the idea, reasonably so. Extraordinary claims require extraordinary evidence, and a star exceeding accepted mass limits definitely qualifies as extraordinary. Some researchers argued the observations still represented multiple unresolved stars masquerading as one object. Others suggested the models used to estimate stellar masses might contain hidden errors. This is one of the healthiest aspects of science, actually. Scientists are often portrayed as dramatically announcing revolutionary discoveries overnight, but reality tends to involve years of skepticism, recalculation, debate, and exhausted people staring at computer models while surviving primarily on caffeine. R136a1 went through exactly that process. The turning point came with increasingly sophisticated observations using instruments capable of separating individual stars inside the crowded cluster core. Telescopes such as the Hubble Space Telescope and later the Very Large Telescope provided dramatically sharper views. Adaptive optics technology also played a major role. Earth's atmosphere distorts incoming starlight, causing stars to twinkle. Lovely for poetry, inconvenient for precision astronomy. Adaptive optic systems compensate for atmospheric turbulence in real time, allowing ground-based telescopes to achieve astonishing clarity. With these tools, astronomers could finally disentangle the crowded heart of R136 properly. And the results were startling. R136a1 was real, not an illusion, not a blended cluster artifact. A genuine single star possessing a mass far beyond previous expectations. One major study published in 2010 estimated that R136a1 may have originally formed with around 320 solar masses, making it the most massive star ever identified. Even after substantial mass loss through stellar winds, the star remained enormously heavy. That announcement caused understandable excitement across astrophysics, because finding an object like R136a1 does more than update a record book. It forces scientists to reconsider how stars form, evolve, and die. Theoretical limits suddenly looked uncertain. Stellar formation models needed revision. Questions multiplied rapidly. Could stars grow even larger under certain conditions? Were giant stars more common in the early universe? How unstable are such objects? And perhaps most dramatically, how exactly does something this massive avoid blowing itself apart immediately? The strange thing is that R136a1 almost does blow itself apart. Its luminosity sits frighteningly close to something called the Eddington limit, the point where outward radiation pressure nearly balances inward gravity. At that threshold, a star becomes precariously unstable. Radiation pushes outward so intensely that the star can begin shedding its outer layers violently. R136a1 exists dangerously close to that boundary all the time. In other words, the star is living near the absolute edge of what stellar physics permits. That realization changed the emotional tone of the discovery somewhat. Astronomers were not merely observing a large star. They were observing an object occupying a narrow, unstable territory between existence and self-destruction, a star too massive for comfort. And perhaps most remarkable of all, R136a1 is young, very young. Most estimates place its age at only around 1 to 2 million years. To put that into perspective, complex human civilization is older than many individual trees currently alive on Earth, while R136a1 is essentially a newborn by stellar standards. But giant stars do not enjoy long lives. The larger the star, the faster fusion consumes fuel in its core. R136a1 burns energy with terrifying intensity. It sacrifices longevity for brilliance. Every second releases enormous amounts of radiation while simultaneously shortening the star's lifespan. If the sun is a carefully managed candle designed for endurance, R136a1 is more like an industrial explosion attempting to impersonate a star. And because it burns so violently, the star is continuously losing mass through stellar winds. These winds are not breezes in the ordinary sense. They are streams of charged particles accelerated outward at millions of kilometers per hour. Over time, R136a1 may lose dozens of solar masses simply by blasting itself into surrounding space. The Tarantula Nebula bears the scars of these processes everywhere. Massive stars shape their environment constantly. Radiation carves cavities into gas clouds. Stellar winds compress nearby regions and trigger new star formation. Supernova explosions send shock waves rippling through the nebula. the region behaves less like a quiet birthplace and more like an ongoing chain reaction, and deep within it, R136a1 continues burning. Even today, astronomers remain fascinated by the object because it represents a natural laboratory for studying the upper extremes of stellar physics. We cannot recreate these conditions on Earth. The temperatures, pressures, and energies involved are beyond any human engineering capability. So instead, scientists observe carefully from afar. They measure spectra, track luminosities, build simulations, test theories, and occasionally discover that the universe is still willing to surprise them. That may be one of the most comforting things about astronomy. No matter how advanced our technology becomes, the cosmos continues producing objects so strange that scientists must pause and rethink their assumptions. R136a1 did exactly that. For years, researchers thought they understood the upper limits of star formation reasonably well. Then the Tarantula Nebula quietly revealed a giant blue star sitting far beyond expectations, radiating millions of times more energy than the Sun while balancing near the edge of physical stability. Not impossible, apparently, just extreme, and once. Astronomers realized such stars could exist. Attention naturally turned toward the environment that created it. Because R136a1 did not form alone. It emerged from one of the most violent stellar nurseries anywhere near the Milky Way, a region where gravity, radiation, and chaos continuously collide inside glowing clouds of gas. If you could somehow travel safely to the Tarantula Nebula and observe it from nearby, the first thing you would probably notice is that the universe is much brighter than it has any right to be. Not bright in the gentle way we usually imagine space. Popular artwork often shows quiet star fields scattered across peaceful darkness, as though the cosmos is mostly calm with occasional decorative sparkles. Real star-forming regions are nothing like that. Especially not this one. The Tarantula Nebula is loud. Not literally, of course. Space itself carries no sound because there is no atmosphere for pressure waves to move through. Yet visually, physically, energetically, the place behaves like a cosmic storm system operating at catastrophic intensity. Gas clouds glow violently under radiation. Shock waves tear through space. Young stars blast ultraviolet light outward with enough force to reshape entire regions around them. Even the name sounds slightly dangerous. The Tarantula Nebula. It earned that title because of its sprawling filament structure. Long glowing tendrils of gas stretch outward from the central region, resembling the legs of an enormous spider. Through telescopes, the nebula appears tangled and restless, full of arcs, cavities, and luminous knots where stars continue forming. Astronomers catalogue it as 30 Doradus, though honestly the more dramatic nickname feels appropriate here. Because this is not merely another cloud floating quietly through space. It is the most active nearby star-forming region in our local galactic neighbourhood. A gigantic factory where gravity continuously assembles new stars, while older massive stars simultaneously destroy the clouds that created them. And somewhere deep in that chaos sits R136a1, one of the most extreme stellar objects ever discovered. But to understand how a star like R136a1 could form at all, we first need to understand the environment surrounding it. Because giant stars do not emerge from calm conditions. They are born in crowded, unstable places where enormous quantities of gas collapse under gravity all at once. The Tarantula Nebula exists inside the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. Compared to the Milky Way, the Large Magellanic Cloud is smaller and somewhat irregular in shape, looking less like a graceful spiral and more like a galaxy still trying to organise itself after moving apartments. Yet despite its smaller size, it contains extraordinary regions of star formation. The Tarantula Nebula alone spans roughly 1,000 light-years across. That number becomes easier to appreciate when you remember that 1 light-year equals about 9.5 trillion kilometres. So the nebula stretches across distances so enormous that even light itself requires centuries to cross from one side to the other, and throughout much of that vast region, stars are actively being born. Star formation begins inside cold molecular clouds, enormous accumulations of hydrogen gas mixed with helium and traces of heavier elements. These clouds appear dark and quiet from afar, but internally they are unstable. Gravity constantly pulls material inward. Small density variations grow larger over time. Regions begin collapsing. As the gas compresses, temperatures rise. Eventually, if enough material gathers together, pressure inside the forming protostar becomes so extreme that hydrogen fusion ignites in the core. A star is born. Simple in theory, completely terrifying in practice. Because once massive stars ignite, they immediately begin changing everything around them. Young giant stars release astonishing amounts of ultraviolet radiation. That radiation ionizes nearby hydrogen gas, stripping electrons from atoms and causing the surrounding nebula to glow. The beautiful pink and red colours seen in astronomical images are actually signatures of excited hydrogen atoms, releasing energy after being blasted apart by starlight. So in a very literal sense, the nebula shines because nearby stars are violently attacking it. There is something wonderfully aggressive about that process. The Tarantula Nebula contains thousands upon thousands of young stars, many far larger than the Sun. Entire clusters burn inside dense regions of gas. Radiation floods outward continuously. Stellar winds collide. Cavities form where giant stars have cleared away surrounding material like cosmic leaf blowers, operating at several million kilometers per hour. And still, new stars continue forming. That balance between creation and destruction defines stellar nurseries. Massive stars are deeply disruptive neighbours. Their radiation compresses nearby gas clouds, sometimes triggering new collapse events and creating additional stars. At the same time, they also erode and disperse the very clouds needed for future star formation. They are builders and destroyers simultaneously. The central region of the Tarantula Nebula contains a particularly dense cluster, known as R136. This cluster is astonishingly crowded. Thousands of stars occupy a relatively compact region of space, packed together so tightly that the night sky from inside the cluster would be almost incomprehensibly bright. Imagine standing on a hypothetical planet there, assuming such a planet could survive the radiation long enough for sightseeing, which seems optimistic. The sky would not resemble Earth's peaceful darkness sprinkled with distant stars. Instead, enormous blue-white suns would blaze overhead continuously, some brighter than full daylight, others casting overlapping shadows across the landscape, except there probably would not be landscapes, or planets, or landscapes capable of surviving giant radiation storms. Still, the image gives some sense of the scale involved. R136 alone contains many stars exceeding 50 or even 100 solar masses. That is extraordinarily unusual. Most stars in the universe are far smaller. Red dwarfs dominate stellar populations because nature seems to prefer efficiency over spectacle most of the time. Massive stars are rare precisely because forming them is difficult. Gravity must gather enormous quantities of material before radiation pressure interrupts the process. Conditions must remain dense enough for continued accretion. The forming star must avoid blowing away its own fuel supply too early. In calmer regions of space, this becomes challenging, but the Tarantula Nebula is not calm. The sheer amount of available gas there allows gravity to construct truly gigantic stars before radiation can halt the collapse entirely. It is essentially a perfect breeding ground for cosmic excess, and that excess changes everything around it. One of the strangest things about giant stellar nurseries is how dynamic they are. Human intuition tends to imagine the night sky as fixed and unchanging because stars appear stable over our lifetimes. Yet regions like the Tarantula Nebula are evolving continuously. Shock waves ripple outward from supernova explosions, gas clouds collapse, radiation sculpts enormous cavities, stars form in waves, Entire regions brighten and fade over millions of years. The nebula behaves less like a static object and more like weather operating on galactic scales. In fact, many structures visible inside the Tarantula Nebula are temporary. Pillars of gas shaped by radiation may eventually evaporate completely. Dense knots of material may collapse into future star systems. Cavities carved by stellar winds will expand and merge. Nothing there truly rests, and at the centre of much of this activity lies R136. The cluster itself is remarkably young, only around 1 to 2 million years old. That youth matters because giant stars live fast and die quickly. The presence of extremely massive stars tells astronomers they are observing the region during a narrow window in time before the most unstable giants explode. In cosmic terms, we are catching the Tarantula Nebula mid-conversation, and what a conversation it is. The energy released from R136 and neighbouring stars is almost difficult to express meaningfully. Radiation from these stars ionizes enormous volumes of gas across the nebula. Stellar winds eject matter outward at speeds exceeding thousands of kilometers per second. Some stars lose the equivalent of Earth's mass many times over every single year. That detail is worth pausing on briefly. Our planet weighs about 6 sextillion tons, a rather respectable quantity of planet, all things considered. Some massive stars can lose material equivalent to multiple Earths every year simply because their radiation is so intense that the outer layers cannot remain fully bound by gravity. R136a1 belongs firmly in that category. The star continuously sheds mass through violent stellar winds. Charged particles stream away from its surface at extraordinary speeds, colliding with surrounding gas and helping shape the nebula itself. In this sense, giant stars do not merely exist inside stellar nurseries, they engineer them. The Tarantula Nebula's structure reflects generations of massive stars altering their environment. Older stars exploded as supernovae long ago, compressing nearby clouds and triggering new star formation. Younger stars now continue the process through radiation and stellar winds. The result resembles a chain reaction spanning millions of years, and yet, despite all this violence, the nebula is also strangely beautiful. Astronomical images reveal enormous glowing curtains of gas illuminated in pink, blue and gold. Dark dust lanes cut across luminous regions like smoke drifting through coloured light. Dense knots of material appear almost sculpted. Of course, those colours are partly artistic representations adjusted for visibility and wavelength mapping. Human eyes would not perceive the nebula exactly this way in person. Still, the underlying structures are real, and the scale is overwhelming. Some individual cavities inside the Tarantula Nebula span dozens or even hundreds of light years. Entire star clusters fit comfortably within them. Radiation from giant stars sweeps across distances so vast that human language begins struggling to maintain emotional connection to the numbers. This is one reason astronomy often feels strangely calming despite dealing with catastrophic forces. The scales involved exceed ordinary human anxiety. Problems that feel enormous during the day shrink somewhat when placed beside a glowing nebula hundreds of light years wide. Deadlines become less intimidating compared to stellar winds travelling millions of kilometres per hour. Traffic seems less emotionally significant when giant stars are busy detonating nearby molecular clouds. Even insomnia feels slightly less dramatic when you remember the universe contains regions where radiation storms continuously sculpt gas into new suns, and perhaps that is part of why people find comfort in astronomy at night. The cosmos does not erase human concerns, but it changes their proportions. Still, the Tarantula Nebula also reminds us how unusual our own solar system really is. The Sun formed in a much calmer environment, not entirely peaceful, certainly. Evidence suggests nearby supernovae may have influenced the early solar system. But compared to R136, our stellar neighbourhood is remarkably quiet. That quiet matters. Massive stars can severely disrupt planetary formation. Intense radiation strips atmospheres, Stellar winds destabilize surrounding disks of material. Supernova explosions flood nearby regions with energetic particles. Inside dense star clusters like R136, stable long-term planetary systems may be difficult to maintain. So while giant stellar nurseries produce spectacular stars, they may not be ideal places for civilizations hoping to quietly evolve over billions of years without being sterilized by neighboring hypergiants. Earth benefits enormously from orbiting an ordinary middle-aged star rather than something like R136a1, which is fortunate because replacing the Sun with R136a1 would create a number of environmental concerns difficult to solve with renewable energy initiatives. The Tarantula Nebula also offers astronomers a glimpse into conditions more common in the early universe. Billions of years ago, star formation rates across galaxies were often far higher than they are today. Giant dense clusters may have been much more common. Massive stars likely played a crucial role in shaping young galaxies through radiation, supernova explosions, and chemical enrichment. In many ways, the Tarantula Nebula acts like a nearby laboratory for studying that ancient cosmic era. And R136a1 may represent an echo of those early giant stars, because the truly massive stars formed shortly after the Big Bang were probably even larger than modern examples. Astronomers sometimes call them population 3 stars, hypothetical first-generation stars formed almost entirely from hydrogen and helium before heavier elements existed in abundance. These primordial stars may have reached staggering masses. Some models suggest hundreds of solar masses, possibly more. If so, they would have lived brief, violent lives before exploding and seeding the universe with heavier elements necessary for planets, chemistry, and eventually biology. Without giant stars, there would be no carbon, no oxygen-rich atmospheres, no rocky worlds, no humans lying awake at night listening to sleepy astronomy videos while wondering whether the universe is comforting or terrifying. Possibly both. And that brings us back again to R136a1, because inside the Tarantula Nebula, among all the glowing gas and clustered stars, astronomers discovered an object seemingly balanced near the upper edge of what nature permits. A star so massive that even now, scientists continue debating how large stars can truly become before instability tears them apart completely. The environment around R136a1 helped create it. Extreme density, enormous gas reserves, violent star formation, crowded stellar neighborhoods, all the conditions necessary for gravity to assemble something extraordinary before radiation pushed back too hard. And yet, despite those perfect conditions, stars this massive remain incredibly rare. Which raises another question. If R136a1 sits near the upper boundary of stellar mass, what exactly determines that limit? Why can gravity construct giant stars at all, but only up to a certain point before physics begins resisting the process itself? For a long time, astronomers believed they already had a fairly reasonable answer to the question of how massive a star could become. Not an exact answer, certainly. The universe rarely provides those without complications. But there seemed to be a general upper boundary, a point where physics itself would intervene and say, politely but firmly, no, that is quite enough star for one object. Then R136a1 arrived, and behaved like it had not read the guidelines. The problem starts with gravity. Stars form because enormous clouds of gas collapse inward under their own weight. Gravity pulls hydrogen atoms together. As the cloud compresses, the center grows hotter and denser. Eventually, temperatures become high enough for nuclear fusion to ignite. Hydrogen nuclei begin smashing together to form helium, releasing enormous amounts of energy in the process. That outward energy creates pressure, and from that moment onward, a star exists in a kind of constant argument with itself. Gravity tries to crush the star inward. Radiation and pressure push outward. As long as those forces remain balanced, the star survives. Even our sun works this way. Every second, gravity attempts to compress the sun further, while fusion in the core pushes back. The result is a stable middle-aged star quietly converting about 600 million tons of hydrogen into helium every second. Which sounds excessive until you remember the sun contains enough fuel to continue doing this for billions more years. But larger stars behave differently. The more massive a star becomes, the greater the pressure inside its core. Higher pressure means higher temperatures. Higher temperatures make fusion occur dramatically faster, and faster fusion produces vastly more radiation. This creates a problem. At some point, the radiation generated by the star becomes so intense that it starts actively resisting further growth. Imagine trying to inflate a balloon while someone inside the balloon continuously fires leaf blowers outward through the rubber. Eventually, adding more material becomes extremely difficult because the outward force prevents additional gas from settling onto the forming star. Massive stars face exactly this issue. As a protostar grows larger and brighter, its radiation pressure increases sharply. Ultraviolet light pushes against incoming gas. Stellar winds begin ejecting matter outward. The forming star starts disrupting the very cloud feeding its growth. For decades, astronomers believed this naturally imposed an upper mass limit somewhere around 100 to 150 times the mass of the Sun. That estimate made sense mathematically. It made sense observationally. And perhaps most importantly, it made scientists emotionally comfortable because the universe appeared to be behaving in an organized and predictable manner. Then astronomers looked more carefully at the R136 inside the Tarantula Nebula, and suddenly the numbers stopped cooperating. R136a1 appeared far too massive, not slightly above expectations, not comfortably within measurement uncertainty, wildly above the accepted limit. At first, many researchers understandably suspected observational errors. Perhaps several stars blended together into one unresolved object. Perhaps the luminosity estimates were inaccurate. Perhaps the stellar evolution models needed adjustment. All reasonable possibilities. But as telescope resolution improved and more detailed spectroscopic analysis accumulated, the conclusion became increasingly unavoidable. R136a1 genuinely seemed to possess an initial mass exceeding 300 solar masses, which raised an uncomfortable possibility. Maybe stars could become much larger than theorists previously believed? Now that does not mean there is no upper limit at all. Physics still imposes boundaries. The universe enjoys chaos, certainly, but it also respects equations most of the time. The challenge lies in understanding where those boundaries actually sit and how giant stars manage to approach them. One major concept involved here is something called the Eddington limit. The Eddington limit represents the point where outward radiation pressure from a star nearly balances the inward pull of gravity. If a star exceeds this threshold too dramatically, radiation begins pushing matter away faster than gravity can hold it together. Essentially, the star starts blowing itself apart. It's an extraordinary balancing act. Too little pressure and gravity crushes the star inward. Too much luminosity and the outer layers become unstable. Stars survive only because these forces remain delicately matched. For ordinary stars like the Sun, this balance is relatively calm and stable, but giant stars live dangerously close to the Eddington limit almost constantly. R136a1 especially. Its luminosity is so extreme that radiation pressure continuously drives powerful stellar winds away from the surface. The star loses enormous amounts of material every year simply because its own light is too violent to fully contain itself. In a sense, R136a1 exists in a permanent state of controlled instability, and yet it survives, at least for now. One reason giant stars can still form despite intense radiation pressure involves geometry. Early simplified models assumed gas fell evenly onto the protostar from all directions. Under those conditions, radiation pressure would halt growth fairly quickly. Real star formation is messier. Gas often collapses through dense disks and filament structures. Magnetic fields influence flows. Some regions shield incoming material from radiation temporarily. Matter can continue feeding the star unevenly through concentrated channels even while radiation blasts other regions outward. Instead of a neat spherical collapse, giant star formation resembles a chaotic traffic jam occurring inside a hurricane while several explosions happen nearby. Nature, it turns out, is surprisingly resourceful when building excessive objects. Another factor involves stellar mergers. Dense clusters like R136 contain enormous numbers of stars packed close together. Under such crowded conditions, collisions and mergers between young massive stars may occur. Two already large stars can combine into an even larger object, temporarily bypassing formation limits that would constrain a single collapsing protostar. Some astronomers suspect R136a1 may partly owe its extraordinary mass to such mergers. That possibility adds another layer of chaos to the story. Imagine giant stars forming in crowded environments, spiraling together, colliding, and producing even larger unstable objects radiating with terrifying intensity. Stellar nurseries begin sounding less like peaceful birthplaces and more like demolition derbies operating under relativistic conditions. And perhaps that is not entirely inaccurate. Massive star clusters are violent environments. Radiation floods outward continuously. Shock waves ripple through gas. Gravity reshapes entire regions. Supernovae eventually detonate nearby. Under such conditions, unusual outcomes become more likely. Still, even if mergers help explain stars like R136a1, the object remains extraordinary because sustaining such a massive star is itself difficult. The larger the star becomes, the shorter its lifespan. This is one of the strangest truths in stellar physics, because it feels backwards intuitively. Human instincts often associate larger size with greater endurance, larger fuel tank, longer lifespan. Stars disagree. A small red dwarf star can survive for trillions of years because it burns fuel slowly and efficiently. Massive stars burn with astonishing wastefulness. Their cores become so hot that fusion proceeds at incredible rates. Enormous energy output means enormous fuel consumption. R136a1 burns through nuclear fuel with almost reckless extravagance. If the Sun is a careful long-distance runner conserving energy, R136a1 is sprinting full speed through existence while setting parts of itself on fire. And because these giant stars are so luminous, they also suffer catastrophic mass loss. The Sun emits a solar wind, certainly, but compared to R136a1 it is relatively gentle. Giant hypermassive stars eject material at enormous rates. Their stellar winds can travel millions of kilometers per hour and remove substantial fractions of the star's mass over time. In fact, R136a1 has probably already lost dozens of solar masses since formation. That detail reveals something important. When astronomers estimate the star originally formed with perhaps 300 solar masses or more, they are not observing the object at peak size anymore. They're observing it after substantial erosion by its own radiation. The star is actively dismantling itself, and this raises another fascinating question. If stars this large are so unstable, why does the universe build them at all? The answer may involve efficiency on cosmic scales. Massive stars profoundly shape galaxies despite their short lives. Their radiation ionizes enormous regions of space. Their stellar winds redistribute gas clouds. Their eventual supernova explosions forge heavy elements and trigger new waves of star formation. A single giant star can influence entire stellar neighborhoods. Without massive stars, galaxies would evolve very differently. The universe seems willing to tolerate brief periods of instability because giant stars perform important chemical and structural work. They are cosmic accelerators, factories for heavy elements, engines driving galactic evolution. And perhaps nowhere is this clearer than in the early universe. Shortly after the Big Bang, conditions differed dramatically from today. The universe contained mostly hydrogen and helium. Heavy elements had not yet accumulated because stars had not existed long enough to manufacture them. Astronomers suspect the first generation of stars, often called population 3 stars, may have reached truly enormous masses under those conditions, possibly several hundred solar masses, maybe more. Why? Because heavier elements help cool collapsing gas clouds. Without them, primordial gas behaved differently during star formation. Larger fragments may have collapsed directly into giant stars more easily. In other words, the early universe may have specialized in building monsters. R136a1 might represent a modern echo of those ancient giants. Not identical, certainly. The Tarantula Nebula already contains enriched material from earlier generations of stars, but objects like R136a1 help astronomers study physics relevant to those primordial cosmic eras. That connection matters because giant stars likely transformed the young universe dramatically. Their radiation helped reionize cosmic gas. Their explosions forged the first heavy elements. Their deaths may have produced early black holes that later grew into supermassive galactic centers. So while giant stars are rare today, they may once have been much more influential. And yet even modern astronomy still struggles to pin down the exact upper stellar mass limit. Some researchers suggest stars may briefly exceed 300 solar masses under extreme conditions. Others argue instability and mass loss rapidly reduce such objects before they remain observable for long. There may not even be one universal limit. Conditions inside different galaxies can affect star formation. Metallicity, meaning the abundance of heavier elements, changes how gas cools and how stellar winds behave. Interestingly, lower metallicity environments may permit larger stars because weaker stellar winds remove less mass during formation. The Large Magellanic Cloud, home to the Tarantula Nebula, has lower metallicity than the Milky Way. That may partly explain why giant stars flourish there. The universe, as usual, refuses simple answers. Instead of a clean, hard cutoff, stellar mass appears governed by overlapping processes: gravity pulling inward, radiation pushing outward, gas dynamics feeding collapse, magnetic fields shaping flows, mergers altering growth, stellar winds stripping material away. Every giant star becomes a negotiation between competing forces. R136a1 simply pushes that negotiation near the breaking point. And the closer astronomers examine such stars, the stranger they seem. Because eventually another realization emerges. At these masses, stars stop behaving like scaled-up versions of the Sun. Their internal structure changes, their energy transport changes, their atmospheres become unstable, their radiation dominates everything. A giant star like R136a1 is not just more star. It occupies an entirely different physical regime where ordinary intuition starts failing rapidly. Even defining its surface becomes difficult. The outer layers are driven outward by intense radiation. Powerful winds blur the boundary between star and surrounding space. Matter continuously escapes. Light itself becomes trapped and scattered through dense outflowing material. The star almost resembles a controlled detonation pretending to be a stable object. And remarkably, nature allows this to continue for at least a few million years before collapse or explosion finally ends the performance. Human beings are not naturally equipped to understand large numbers. That is not a criticism. Evolution simply never required our ancestors to emotionally process objects weighing hundreds of times more than the Sun. Survival favored recognizing dangerous animals, remembering where food was stored, and perhaps developing the ability to stare suspiciously at berries before eating them. Stellar mass calculations were not a major priority on the prehistoric savanna. So when astronomers say that R136a1 may have formed with more than 300 times the mass of the Sun, the statement tends to slide harmlessly past the human brain without fully connecting to anything tangible. 300 suns. The words sound impressive, but what do they actually mean? Well, Let's start with the Sun itself, because even one ordinary star is already absurd beyond reasonable standards. The Sun contains approximately 99.86% of all mass in the solar system. Every planet, moon, asteroid, comet, grain of dust, and confused space probe combined account for only a tiny leftover fraction. Jupiter, the largest planet in the solar system, could fit inside the Sun more than 1,000 times. Earth would fit over 1 million times, and even then the Sun is considered a fairly average star. That fact alone already makes the universe feel slightly untrustworthy. The Sun weighs roughly 2 octillion tons. Written numerically, that becomes a 2 followed by 30 zeros. At a certain point, the quantity stops feeling like a number and starts resembling someone leaning on a keyboard accidentally. Now multiply that by hundreds. That is the estimated birth mass of R136a1. A single star containing more material than entire small stellar systems. And despite those staggering numbers, gravity still manages to hold it together. Barely. The phrase massive star sometimes creates the wrong mental image because people naturally picture enormous swollen objects like balloons or clouds. In reality, mass and size are not identical things in astronomy. Some stars become physically enormous but relatively diffuse, while others contain tremendous mass packed into comparatively compact volumes. R136a1 belongs to the second category. It is not the physically widest known star. Objects like UY Scuti or Stephenson 2-18 may stretch across vastly larger diameters. If placed at the centre of our solar system, some red supergiants would engulf the orbit of Jupiter entirely. R136a1 is different. It is denser with energy, hotter, more compressed, more violent. Imagine comparing a giant soap bubble to a nuclear furnace. One occupies more space, the other contains vastly more concentrated power. That distinction matters because massive stars behave differently internally. Their cores experience crushing gravitational pressure. Temperatures rise to extraordinary levels. Fusion reactions proceed at astonishing rates. The Sun's core temperature reaches about 15 million degrees Celsius. R136a1 likely exceeds tens of millions of degrees in its core. At those temperatures, matter behaves under conditions difficult even for physics to comfortably describe without extensive equations and deeply concerned graduate students. And yet somehow, despite all that pressure and heat, the star does not collapse immediately. That balancing act is one of the strangest achievements of nature. Gravity is relentless. The more mass an object contains, the harder gravity pulls inward. For a star with hundreds of solar masses, inward pressure becomes almost unimaginable. Layers of plasma press downward toward the core continuously with enormous force, but fusion pushes back. Hydrogen nuclei collide and merge into helium, releasing tremendous energy. That energy generates outward pressure strong enough to resist total collapse. A star survives because these two forces remain balanced. Or in RR136a1's case, because they remain balanced just well enough to delay disaster temporarily. The scale of that balance becomes easier to appreciate when you realize that giant stars are effectively self-regulating explosions. Nuclear fusion releases immense energy trying to blow the star apart, while gravity continuously attempts to crush it inward. The star survives in the unstable middle ground, and the larger the star becomes, the more dangerous that equilibrium grows. One of the remarkable things about R136a1 is that it exists close to the upper edge where this balance remains possible at all. At lower masses, stars behave relatively calmly. The Sun, for example, has remained stable for billions of years. It fuses hydrogen steadily and predictably. Solar flares and magnetic storms occur occasionally, certainly, but overall the Sun behaves like a responsible middle-aged appliance designed for long-term operation. R136a1 behaves more like industrial machinery, operating permanently at maximum overload while sparks fly from every direction. The star's luminosity is so extreme that radiation itself begins competing aggressively against gravity. Outward pressure from light becomes enormous. Stellar winds blast matter into surrounding space continuously, and despite losing tremendous amounts of mass, the star still remains gigantic. That fact alone hints at how extraordinary its original size must have been. Current estimates suggest R136a1 may now contain something closer to roughly 170 to 200 solar masses after substantial erosion by stellar winds. Which means the object astronomers currently observe is already a stripped-down version of its former self, a diminished monster. Though admittedly diminished becomes a relative term when discussing stars large enough to destabilize surrounding space through radiation. There is also another important detail hidden inside these mass estimates. Stars are not solid objects. You cannot stand on them. There is no true surface in the ordinary sense. Instead, stars are giant spheres of plasma, matter heated so intensely that electrons separate from atomic nuclei entirely. The material inside behaves more like electrically charged fluid trapped by gravity than anything resembling rock or metal. Trying to imagine the weight of a star therefore becomes tricky because there is no rigid structure holding everything up. Gravity itself maintains the object. Every layer presses inward on the layers beneath it. The deeper you go, the greater the pressure becomes, and in massive stars like R136a1, those pressures reach astonishing extremes. The core exists under conditions so violent that ordinary human intuition simply stops functioning usefully. Hydrogen fusion alone may not dominate for long. Giant stars can fuse progressively heavier elements in layered structures as they evolve. Carbon, oxygen, neon, silicon. Each stage releases energy differently. Each stage shortens the star's remaining lifespan. Massive stars race through nuclear fuel because their cores are so hot and compressed. The Sun can fuse hydrogen for roughly 10 billion years. R136a1 may survive only a few million years total. That difference feels almost unfair. Imagine two vehicles beginning a journey together. One drives carefully and efficiently across a continent. The other accelerates instantly to catastrophic speed while consuming fuel like a small nation during an energy crisis. The second vehicle travels brilliantly for a short time before something explodes. That is essentially how giant stars live. And because R136a1 burns with such extraordinary intensity, its internal structure becomes highly turbulent. Convection currents churn through the star. Radiation pressure destabilizes outer layers. Material circulates differently than in smaller stars. Some regions inside may complete mixing processes that smaller stars never experience. In ordinary stars like the Sun, different layers can remain relatively separated over time. In extremely massive stars, internal turbulence becomes so powerful that large portions of the star may mix together more efficiently. This changes stellar evolution dramatically. Fresh hydrogen gets transported inward. Fusion processes continue differently. The star's lifetime and future collapse become more complicated. Astronomers studying R136a1 are therefore not merely observing a larger version of the Sun, they are studying a fundamentally different category of stellar physics, operating near the limits of stability. And all of this occurs while the star continuously loses material through stellar winds. Those winds deserve a moment of appreciation because they are among the most violent steady outflows in the universe. The Sun emits a solar wind too. Earth experiences its effects through auroras and magnetic storms. But compared to R136a1, the Sun's wind is almost gentle. R136a1 ejects matter outward at speeds reaching thousands of kilometers per second. Every second, enormous streams of charged particles blast away from the star. These winds are driven by radiation itself. Light emerging from the star carries momentum. In stars, this luminous photons exert enough force on surrounding material to physically accelerate gas outward into space. Imagine sunlight becoming so intense that it literally blows pieces of the star away. That is happening continuously. Over time, the star sheds huge amounts of mass into the surrounding nebula. The Tarantula Nebula around R136a1 bears evidence of these interactions everywhere. Radiation sculpts nearby gas clouds. Stellar winds carve cavities into the nebula. Shock fronts ripple through surrounding material. The star actively reshapes its environment. And perhaps the strangest thing of all is that even giant stars like R136a1 are still tiny compared to galaxies. Astronomy constantly plays this psychological trick on us. A star massive enough to contain hundreds of suns feels overwhelmingly large until you zoom outward again. Then, the Tarantula Nebula dwarfs the star cluster. The Large Magellanic Cloud dwarfs the nebula. The Milky Way dwarfs the neighbouring galaxy. Local galaxy groups dwarf the Milky Way. Scale keeps escalating. Still, within the category of individual stars, R136a1 occupies extraordinary territory. Most stars are tiny red dwarfs containing only fractions of the Sun's mass. Even among giant stars, objects exceeding 100 solar masses remain extremely rare. Nature strongly favours smaller, longer-lived stars because they form more easily and survive vastly longer. Massive stars represent exceptions, brief extravagant bursts of cosmic excess, and yet those rare giants play enormous roles in shaping the universe. Their radiation alters surrounding gas clouds. Their winds redistribute material. Their eventual deaths forge heavy elements necessary for planets and biology. Without giant stars, the universe would remain chemically primitive. No carbon-rich chemistry. No oxygen-heavy atmospheres. No rocky planets. No living organisms capable of wondering how large stars can become. In a very literal sense, objects like R136a1 help make future life possible by dying violently enough to scatter enriched material across space, which is both comforting and slightly alarming, and eventually every giant star reaches a point where sheer mass becomes a curse rather than an advantage. Because gravity always waits patiently. Fusion can resist collapse only temporarily. The larger the star, the more difficult long-term stability becomes. One day the core changes, fuel runs low, fusion slows, gravity begins winning, and for giant stars that ending does not arrive gently. R136a1 carries so much mass that its eventual death may produce one of the most energetic stellar catastrophes imaginable. Supernova, hypernova, perhaps direct collapse into a black hole. Astronomers still debate exactly how such enormous stars end their lives, because nature provides relatively few examples to study clearly, but one thing seems certain. When a star this massive dies, the universe notices. If mass tells us how much star exists, luminosity tells us how violently that star is living. And in the case of R136a1, the answer is violently enough to make ordinary stars seem almost restrained. Even the Sun, impressive as it is, suddenly begins looking cautious by comparison, responsible, economical, like a sensible household appliance humming quietly in the corner, while R136a1 behaves more like a cosmic industrial accident that somehow achieved self-awareness, because R136a1 does not merely shine. It unleashes energy at a rate so extreme that human intuition struggles to keep pace with the numbers. The Sun produces roughly 3.8 times 10 to the 26th power watts of power every second. That is already an absurd quantity of energy. In 1 second, the Sun emits more energy than human civilization has consumed throughout all of recorded history, combined many trillions of times over, and yet R136a1 radiates millions of times more energy than the Sun. Not slightly brighter, not modestly brighter, millions. At that scale, the word bright almost stops being useful. Astronomers estimate R136a1 may shine with nearly 10 million times the luminosity of our Sun. If the Sun were represented by a single candle, R136a1 would resemble an entire city viewed from orbit during a continental power surge, and all of this energy comes from fusion occurring deep inside the star's core. That is one of the strangest facts about stars. They are powered by the same basic process that humans attempt to recreate experimentally in fusion reactors on Earth. Hydrogen nuclei collide under enormous pressure and temperature, merging into helium while releasing energy according to Einstein's famous equation, E equals mc square A. Tiny amount of mass converts directly into energy. Inside the Sun, this process proceeds steadily and relatively efficiently. The Sun converts around 600 million tons of hydrogen every second. Roughly 4 million tons of that mass become pure energy, which sounds dramatic because it is. But inside R136a1, fusion occurs under much more extreme conditions. The star's enormous mass creates crushing gravitational pressure in the core. Higher pressure means higher temperatures. Higher temperatures mean atomic nuclei collide more violently and more frequently. Fusion accelerates enormously. As a result, R136a1 burns through fuel at terrifying speed. The Sun can survive for around 10 billion years because it burns carefully. R136a1 is effectively throwing nuclear reactions at the problem continuously while sprinting toward destruction. Its total lifespan may only last a few million years. That difference reveals something fundamental about stellar physics. Stars do not scale gently. Doubling the mass of a star does not merely double its brightness. Luminosity rises much faster than mass. Giant stars become disproportionately more energetic as they grow larger, and eventually, objects like R136a1 approach levels where radiation itself begins destabilizing the star. To understand why, we need to talk about temperature. The Sun's surface temperature sits around 5,500 degrees Celsius, hot enough to vaporize absolutely everything humans have ever built without the slightest hesitation, hot enough that even imagining direct contact feels emotionally unreasonable. Yet by stellar standards, the Sun is fairly moderate. R136a1 reaches surface temperatures exceeding 50,000 degrees Celsius. Some estimates push even higher. At those temperatures, matter behaves under astonishing conditions. Atoms become heavily ionized. Radiation floods outward primarily in ultraviolet wavelengths. The star glows blue-white because hotter objects emit shorter wavelengths of light. This is one of those fascinating astronomical details invisible to everyday experience. Humans instinctively associate red with hotter temperatures because of fire and heated metal. But in stellar physics, blue stars are hotter than red stars. A red star is relatively cool. A blue star is terrifying, and R136a1 belongs firmly in the terrifying category. Its surface emits enormous amounts of ultraviolet radiation, far more energetic than visible light. If Earth somehow orbited nearby, the atmosphere would not survive. Radiation would strip molecules apart rapidly. Oceans would evaporate. Surface temperatures would become catastrophic long before anyone had time to complain about sunscreen. Even at enormous distances, giant stars profoundly affect surrounding space. Inside the Tarantula Nebula, R136a1, and neighbouring massive stars flood the region with ultraviolet radiation powerful enough to ionize huge clouds of hydrogen gas. That is why the nebula glows so brightly. The gas itself is responding to constant bombardment from nearby giant stars. In a sense, the nebula is fluorescing beneath stellar violence. And perhaps the strangest part is that visible light represents only a small fraction of the energy involved. Stars like R136a1 emit enormous quantities of ultraviolet radiation, X-rays, and energetic stellar winds. Their influence extends far beyond what human eyes could safely perceive. The energy output is so intense that the star continuously strips away its own outer layers. This happens because photons carry momentum. Ordinarily, light feels weightless to us. Sunlight warms your skin but does not physically shove you backward across the room, which is probably for the best socially. But in giant stars, the sheer number of photons becomes overwhelming. Radiation pressure grows enormous. Every second, vast streams of light push outward from the star's interior, colliding with surrounding plasma and accelerating material into space. The result is a stellar wind so powerful that R136a1 loses mass continuously. The star is effectively evaporating through brightness alone. Imagine a bonfire burning so intensely that chunks of the fire itself begin blasting away into the air at millions of kilometers per hour. That is happening constantly. Astronomers estimate R136a1 may lose material at rates millions of times stronger than the solar wind emitted by the Sun. The outflowing particles race into surrounding space, colliding with gas clouds throughout the nebula. And because the star is so luminous, these winds are incredibly fast, thousands of kilometers per second. At those speeds, material expelled from the star could cross Earth in just a few seconds. Of course, there would not be much Earth left after direct exposure to such conditions, but the comparison helps communicate the violence involved. One remarkable thing about giant stars is how unstable they become near the upper mass limit. Smaller stars achieve long-term equilibrium relatively easily. Massive stars struggle constantly against their own energy output. R136a1 exists dangerously close to the Eddington limit, the point where outward radiation pressure nearly equals inward gravity. Near that boundary, even slight changes in internal conditions can destabilize portions of the star. The outer layers become difficult to hold on to. Mass loss increases. Brightness fluctuates. The star begins behaving less like a calm object and more like a controlled catastrophe. And still, somehow it survives, at least temporarily. Inside the core, temperatures reach levels difficult to describe meaningfully without abandoning normal human experience entirely. Tens of millions of degrees, perhaps more. Under such conditions, matter no longer resembles anything familiar. Plasma dominates. Atomic nuclei move at extraordinary speeds. Fusion reactions occur continuously. Energy generated in the core begins a long outward journey toward the surface. That journey itself is astonishing. Photons produced near the center of a star do not travel straight outward immediately. Inside dense stellar interiors, light gets repeatedly absorbed and re-emitted by surrounding matter. A single photon may bounce around randomly for thousands or even millions of years before finally escaping the surface. Which means sunlight striking Earth today may originate from energy generated deep inside the Sun long before humans built pyramids or invented agriculture. Inside R136a1, conditions become even more extreme. Energy transport occurs through complicated combinations of radiation and convection. Turbulent motion stirs stellar material. Immense pressure gradients reshape the internal structure. The star becomes less like a simple glowing sphere and more like a gigantic unstable engine operating near failure. And because the star burns fuel so rapidly, its evolution proceeds much faster than ordinary stars. The Sun spends billions of years fusing hydrogen steadily. R136a1 tears through equivalent stages at astonishing speed. This creates a curious paradox about giant stars. They are among the brightest objects in the universe, yet they live some of the shortest lives. Brilliance and fragility become deeply connected. A red dwarf star may survive for trillions of years precisely because it burns slowly and efficiently. R136a1 sacrifices longevity for extraordinary luminosity. It spends energy recklessly, almost extravagantly. There is something oddly human about that behavior. Not scientifically, certainly. Stars do not possess intentions or personalities, but emotionally giant stars feel dramatic, temporary, excessive. They blaze with astonishing intensity before collapsing quickly compared to calmer stellar neighbours. And because these stars are so luminous, they dominate their environments completely. If R136a1 replaced the Sun, Earth would not simply become warmer. The entire architecture of the solar system would change. Radiation pressure alone would disrupt planetary atmospheres. Temperatures would rise beyond survivable levels instantly. The night sky across neighbouring worlds would become permanently bright. Even distant outer planets would receive more energy than Earth currently receives from the Sun. Fortunately, R136a1 resides safely inside the Large Magellanic Cloud, roughly 160,000 light-years away, which gives humanity a comfortable margin for error. Still, observing such stars helps astronomers understand the extremes of nature. The universe permits objects operating at astonishing energy levels, and that energy shapes galaxies. Massive stars ionize surrounding gas clouds. Their stellar winds compress nearby material. Their radiation alters chemistry across entire nebular regions. Eventually, their deaths trigger supernova explosions capable of briefly outshining whole galaxies. Without giant stars, cosmic evolution would proceed very differently. Heavy elements necessary for planets and life would form less efficiently. Galaxies would evolve differently. Even black hole formation might change dramatically. In this sense, stars like R136a1 are not merely curiosities. They are major participants in the evolution of the universe itself, and perhaps the strangest detail of all is that R136a1 is still incredibly young, roughly 1 or 2 million years old. That is almost nothing in cosmic terms. Dinosaurs survived on Earth far longer than that. Some stars near our solar system are thousands of times older. Yet, R136a1 already radiates with unimaginable intensity while actively destroying itself through stellar winds. It is living at maximum speed from the very beginning. That pace cannot continue forever. Eventually, the hydrogen fuel in the core will diminish. Fusion processes will shift. Internal balance will destabilize further. The star's enormous mass will begin transforming from advantage into burden. And when that happens, the ending may become one of the most violent stellar deaths the universe can produce. But before we reach the collapse itself, there is another important question hidden inside R136a1's extraordinary brightness. How can something so luminous survive at all without immediately tearing itself apart? One of the strangest things about stars is that the biggest ones die first. At first glance, that feels completely backwards. If someone handed you 2 candles, one small and one enormous, you would probably assume the larger candle lasts longer. More wax, more fuel, more endurance. That logic works perfectly well for ordinary objects on Earth. Stars, however, operate according to a far less emotionally reassuring system. In stellar physics, having more fuel often means destroying it much faster. And no known star demonstrates that more dramatically than R136a1. Despite containing hundreds of times the mass of the Sun and producing millions of times more energy, R136a1 may survive only a few million years before reaching catastrophic collapse. Meanwhile, tiny red dwarf stars elsewhere in the universe will quietly continue glowing for trillions of years, long after galaxies themselves begin changing shape. The universe, it seems, rewards moderation. Giant stars ignore moderation entirely. To understand why, we need to return once again to gravity, because gravity controls nearly everything stars do. It determines how they form, how hot their cores become, how quickly fusion occurs, and ultimately how they die. When a star forms, gravity pulls enormous quantities of gas inward. The more mass the star gathers, the stronger gravity becomes. That stronger gravity compresses the core more intensely, increasing both pressure and temperature, and fusion reactions are extremely sensitive to temperature. A modest increase in core temperature can dramatically accelerate fusion rates. This is where giant stars begin getting themselves into trouble. The Sun's core temperature reaches around 15 million degrees Celsius. Under those conditions, hydrogen nuclei fuse steadily into helium through a process called the proton-proton chain. The reactions occur slowly enough that the Sun can maintain stability for roughly 10 billion years. R136a1 operates under vastly more extreme conditions. Its enormous gravitational pressure drives core temperatures far higher. Fusion accelerates enormously. Energy floods outward at astonishing rates. Radiation pressure grows intense. Luminosity skyrockets. And fuel consumption becomes absolutely reckless. The relationship between stellar mass and lifespan is deeply uneven. A star twice as massive as the Sun does not live half as long. It may live only a fraction as long because luminosity rises dramatically with increasing mass. Massive stars burn disproportionately brighter, and brightness represents energy expenditure. A useful analogy might involve engines. Imagine two vehicles. One drives carefully at efficient speed, conserving fuel for a long journey. The other operates permanently at maximum acceleration, with the engine screaming continuously while parts fall off behind it on the highway. R136a1 is very much the second vehicle. The star generates so much energy that it tears through nuclear fuel with astonishing speed. Every second, enormous quantities of hydrogen fuse inside the core. Radiation pours outward. Stellar winds eject mass into surrounding space. The star is essentially spending its entire existence in emergency overdrive, and because it burns so intensely, it evolves rapidly. Ordinary stars progress through relatively stable phases lasting billions of years. Giant stars race through evolutionary stages almost recklessly. Core conditions change quickly. New fusion processes ignite sooner. Instability develops earlier. It is rather like comparing a slow-burning campfire to an industrial blast furnace operating without safety regulations. There is also another important detail here. Massive stars are not especially efficient. That sounds strange initially, because giant stars seem overwhelmingly powerful, yet efficiency and power are not the same thing. A fuel-efficient car conserves energy carefully. A drag racer produces extraordinary output while consuming enormous quantities of fuel rapidly. Massive stars behave like cosmic drag racers. They generate incredible luminosity, but the cost is shortened lifespan. And in the case of R136a1, the cost becomes extreme. Astronomers estimate the star may only survive around 2 to 3 million years total before collapsing or exploding. Some estimates vary slightly, but regardless of the exact number, the lifespan remains astonishingly short by stellar standards. For perspective, the Sun is roughly 4.6 billion years old. Earth itself formed billions of years ago. Complex life evolves slowly across immense stretches of time. R136a1 may complete its entire existence in less time than some geological features on Earth remain stable. That brevity changes how astronomers think about giant stars. When observing R136a1, scientists are witnessing a very temporary phenomenon. The star exists during a narrow cosmic moment before instability eventually overwhelms it. In fact, the star has already spent a significant portion of its likely lifespan, and it is still extremely young. That combination feels almost paradoxical. Young in age, old in stellar exhaustion. Because giant stars age rapidly internally, fusion inside a star creates a delicate balancing act between outward pressure and inward gravity. As long as hydrogen fusion continues efficiently in the core, the star remains relatively stable, but hydrogen cannot last forever. Eventually the core composition changes, helium accumulates, temperatures rise further, new fusion processes begin. In smaller stars like the Sun, these transitions occur gradually across billions of years. In massive stars, they happen rapidly and violently. The star races from one fusion stage to the next, because the core conditions are already so extreme. and each new stage becomes shorter than the previous one. Hydrogen fusion lasts longest, helium fusion proceeds faster, carbon fusion accelerates further. Oxygen and silicon fusion can occur astonishingly quickly near the end. For the most massive stars, final fusion stages may last mere days before collapse. Imagine a giant star spending millions of years preparing for disaster, then suddenly racing through its final internal transformations almost frantically. That is essentially what happens. R136a1 is currently burning hydrogen primarily, but eventually it will move toward heavier fusion processes if enough mass remains after stellar winds strip material away. And those stellar winds are another reason giant stars live short lives. The Sun loses some material through the solar wind, certainly, but compared to R136a1, the Sun's mass loss is almost polite. R136a1 blasts matter into surrounding space continuously through radiation-driven winds. The star is so luminous that photons themselves push enormous amounts of material outward. This means the star is not only burning fuel rapidly internally, it is also physically throwing portions of itself away. Every year, tremendous quantities of stellar material escape into the surrounding Tarantula Nebula. Over time, the cumulative mass loss becomes enormous. Astronomers believe R136a1 may have already shed dozens of solar masses since formation. That detail matters because stellar mass strongly influences evolution. As the star loses mass, its structure changes, luminosity changes, internal fusion dynamics shift. The star evolves not just because it burns fuel, but because it literally becomes smaller over time. In some ways, giant stars spend their lives eroding themselves, and the closer they move toward instability, the more dramatic the process becomes. Massive stars also experience much stronger internal turbulence than smaller stars. Convection churns material through the interior. Layers mix differently. Radiation pressure creates instability throughout the structure. The result is a star constantly struggling to maintain equilibrium. Smaller stars enjoy relatively quiet internal lives. R136a1 lives in permanent crisis management. Even the star's surface reflects this instability. Outer layers become difficult to define clearly because powerful winds blur the distinction between star and surrounding space. Material continuously streams outward at tremendous speeds. In a sense, giant stars are partially dissolving while they live, and yet despite all this instability, they remain profoundly important to the universe. In fact, giant stars may matter disproportionately precisely because they live fast and die young. Short-lived massive stars dominate their environments dramatically. Their radiation ionizes surrounding gas clouds. Their winds compress nearby material. Their eventual explosions scatter heavy elements across space. A single giant star can reshape entire regions of a galaxy. This sun influences the solar system. R136a1 influences a nebula hundreds of light years wide. That difference in scale reflects the enormous energy involved. Massive stars also serve as cosmic chemical factories. During their brief lives, they fuse heavier and heavier elements inside their cores. When they eventually explode, those elements scatter into space and become part of future stars, planets, and living organisms. Without giant stars, the universe would remain chemically primitive. No iron-rich planets, no oxygen-rich atmospheres, no carbon-based biology. Even the calcium in human bones originated inside ancient stars long dead. That realization never becomes less strange. Every person listening tonight is built partly from material forged inside stars that lived violently and died catastrophically long before Earth existed, and R136a1 is participating in that process right now. The star's future death will eventually seize surrounding space with additional heavy elements. New generations of stars may form from enriched material ejected during its final collapse. Perhaps future planetary systems will emerge partly from its remains. There is something oddly comforting about that cycle, not because giant stellar explosions are peaceful, They definitely are not. But because destruction and creation become intertwined on cosmic scales. Giant stars live briefly precisely because they burn so intensely, and that intensity helps shape future generations of cosmic structure. Still, giant stars themselves experience remarkably lonely lives. Dense star clusters like R136 contain many stars, certainly, yet massive stars outshine their neighbours so completely that they dominate the surrounding region almost immediately. Their radiation floods outward, their winds disrupt nearby gas, their luminosity overwhelms ordinary stellar environments. A star like R136a1 cannot quietly coexist with its surroundings. It changes everything nearby simply by existing. And because the star burns so fast, every moment matters more. A red dwarf can survive so long that the universe itself may fundamentally change before the star dies. R136a1 exists during a brief spectacular flash by comparison. If the universe's history were compressed into a single calendar year, giant stars would appear and vanish almost instantly, while smaller stars endured quietly in the background. There is an interesting emotional contrast there. The most spectacular stars are often the least durable. The longest-lived stars are usually small, dim, and quiet. Nature seems oddly fond of that trade-off, and perhaps nowhere is that more visible than in the final stages awaiting giant stars. Because eventually the fuel runs low, the balance shifts, gravity begins regaining control, and for stars as massive as R136a1, the ending may become unimaginably violent. But before collapse arrives, another process continues shaping the star every second of its existence: the stellar winds. When most people hear the phrase stellar wind, they imagine something gentle, a breeze perhaps, solar air drifting quietly through space, the sort of thing that might lightly disturb a cosmic curtain if the universe happened to own curtains. Real stellar winds are considerably less polite. Even the sun produces a continuous stream of charged particles flowing outward in all directions. This solar wind travels hundreds of kilometers per second and constantly washes across the solar system. Earth's magnetic field shields us from much of it, though some particles still interact with the atmosphere and create auroras near the poles. Those glowing green lights dancing across Arctic skies are, in part, the visible result of Earth surviving an ongoing stream of material blasted outward from the Sun. And yet, compared to the winds from R136a1, the Sun's solar wind begins looking almost delicate. Because R136a1 does not merely emit particles into space, it tears itself apart continuously. Every second, the star blasts enormous quantities of matter outward at extraordinary speeds. These outflows are so violent that they reshape surrounding regions of the Tarantula Nebula, while simultaneously stripping mass away from the star itself. In other words, R136a1 spends its life slowly evaporating through sheer brightness. That sounds dramatic because it is. The reason stellar winds become so powerful in giant stars begins once again with radiation. Massive stars generate astonishing luminosities. Light emerging from the core carries energy, but it also carries momentum. Normally this effect is tiny. You can stand in sunlight without being physically shoved backward across the street, which is fortunate because crossing intersections would become deeply inconvenient. But in stars like R136a1, the amount of radiation becomes enormous. Photons streaming outward collide with matter in the star's outer layers. Atoms absorb and scatter light repeatedly. Momentum transfers into the plasma. The result is outward. Acceleration powerful enough to overcome gravity and portions of the atmosphere. And then the material escapes, continuously, at speeds reaching thousands of kilometers per second. To appreciate how extreme that is, consider that Earth orbits the Sun at roughly 30 kilometers per second. Material from R136a1 can travel outward vastly faster than planetary orbital speeds. The star's wind is less like ordinary air movement and more like an expanding storm of high-energy plasma racing violently into surrounding space. Astronomers estimate R136a1 loses enormous amounts of mass through these winds every year. The exact numbers vary depending on observational models, but the mass loss rates remain astonishing regardless. The star may shed material equivalent to many Earths every single year. Pause for a moment and consider how absurd that statement would sound in almost any other context. Imagine a mountain casually losing multiple planets' worth of material annually while still remaining one of the largest objects nearby. That is effectively what giant stars do. And over time, the losses become enormous. Scientists believe R136a1 originally formed with perhaps over 300 solar masses. Today, estimates place it closer to around 170 to 200 solar masses. A tremendous amount of stellar material has already been blasted away into surrounding space. The star is shrinking because it cannot fully contain its own radiation. There is something almost tragic about that. Not emotionally tragic, certainly. Stars do not possess feelings, but physically, giant stars exist near the edge of stability from the beginning. Their brilliance actively undermines their long-term survival. The brighter they burn, the faster they destroy themselves, and in stars this extreme stellar winds become one of the dominant forces shaping evolution. The Sun's future depends mostly on gradual fusion changes deep in the core. R136a1's future depends heavily on how much mass it manages to lose before final collapse. That distinction matters enormously, because stellar mass determines almost everything about a star's fate. Mass controls core pressure. Core pressure controls temperature. Temperature controls fusion. Fusion controls lifespan and eventual collapse. So when stellar winds strip away huge amounts of material, they alter the star's destiny directly. In fact, some astronomers believe giant stars may avoid certain catastrophic endings precisely because winds remove enough mass before the final stages occur. Without strong winds, stars like R136a1 might remain even more unstable than they already are. Of course, less unstable remains a relative term when discussing objects emitting millions of times more energy than the Sun while dissolving into space. One fascinating aspect of stellar winds is how invisible they would appear to ordinary human senses despite their enormous power. Space itself remains mostly empty. The particles streaming away from R136a1 are spread across enormous volumes. Yet collectively, the outflow carries tremendous momentum and energy. And because the winds collide with surrounding gas inside the Tarantula Nebula, they sculpt enormous structures into the surrounding material. Astronomers observe cavities, shock fronts, and glowing arcs throughout giant stellar nurseries. Many of these features form because stellar winds slam into nearby gas clouds at extraordinary speeds. The effect resembles a hurricane continuously reshaping landscapes, except the hurricane is made of ionized plasma traveling faster than many spacecraft humans have ever built. The environment around R136a1 is therefore deeply chaotic. Radiation floods outward, winds collide, gas clouds compress and expand, shock waves ripple through the nebula, and all of this occurs simultaneously across distances measured in light years. It is easy to forget how dynamic the universe really is because human lifetimes are short compared to cosmic timescales. The stars appear fixed overhead. Constellations seem permanent. Space feels calm and silent. But inside star-forming regions like the Tarantula Nebula, conditions evolve constantly. Massive stars actively reshape their surroundings while racing toward destruction. And stellar winds help drive much of that transformation. Interestingly, the composition of these winds can reveal important clues about what is happening inside the star. As giant stars evolve, fusion products from the interior may become mixed outward toward the surface through turbulence and mass loss. Stellar winds then carry these heavier elements into surrounding space. In a sense, giant stars leak information about their internal processes into the cosmos. Astronomers studying spectral lines in stellar winds can determine which elements are present, how fast the material moves, and how the star itself is evolving. This becomes especially important for Wolf-Rayet stars like R136a1. Wolf-Rayet stars represent an advanced stage of massive stellar evolution, where strong winds expose deeper layers of the star. Their spectra reveal unusual abundances of helium, nitrogen, carbon, or oxygen, depending on evolutionary stage. The star's own atmosphere gets peeled away gradually, exposing material processed by nuclear fusion deep inside. It is rather like watching erosion strip layers from a mountain, except the mountain is made of plasma and emits enough radiation to sterilize planetary systems. The winds from R136a1 are also intensely hot. Not warm in any ordinary sense. The outflowing plasma reaches temperatures of tens of thousands or even millions of degrees in some regions where shocks occur. Charged particles collide violently. Magnetic fields twist and accelerate material further. The result is an environment hostile to almost anything resembling stability. And yet these winds also contribute to future creation. That is one of the most fascinating contradictions in astronomy. Destructive processes often become essential for future structure formation. Stellar winds compress nearby gas clouds, increasing density in some regions. That compression can trigger gravitational collapse and initiate new star formation elsewhere. So while R136a1 destroys itself, it may simultaneously help create future generations of stars nearby. The universe is remarkably efficient at recycling catastrophe. Even supernova explosions function this way. Shockwaves from dying stars can trigger new star formation by compressing surrounding molecular clouds. Destruction creates pressure. Pressure creates collapse. Collapse creates stars. And eventually those stars produce more destruction. The cycle continues. Massive stars also enrich surrounding space chemically through their winds. Material expelled from R136a1 contains heavier elements forged inside the star. Over time, those elements become incorporated into future nebulae, planets, and possibly living organisms. Without giant stars shedding mass, the universe would remain chemically simpler. No carbon-rich worlds, no oxygen atmospheres, no rocky planets capable of supporting biology. Even the iron in human blood originated from stellar processes inside ancient stars, which means your body currently contains atoms forged in environments not entirely unlike the one surrounding R136a1. There is something oddly calming about that connection. The universe feels less distant when you remember that stellar evolution helped make your existence possible at the atomic level. Still, giant stellar winds can also create serious instability for the stars themselves. As R136a1 loses mass, its internal structure changes. Pressure balances shift. Fusion conditions evolve. The star gradually transforms throughout its lifetime, and because the winds are so strong, this transformation happens quickly. Ordinary stars evolve slowly enough that stability dominates most of their existence. Giant stars race through changes rapidly. Some researchers suspect that stars near the upper mass limit may never achieve long-term equilibrium at all. Instead, they might experience episodic eruptions, enhanced mass loss phases, or unstable transitions throughout their lives. There are stars elsewhere in the universe that occasionally brighten dramatically as they eject huge quantities of material. These events can resemble smaller supernovae temporarily. Massive stars behave unpredictably because they live so close to instability. R136a1 likely experiences continuous turbulence beneath its outer layers. Radiation pressure pushes outward aggressively. Stellar winds accelerate matter away constantly. Internal convection churns material through the interior. The star survives through dynamic balance rather than calm stability, and eventually even those enormous winds may not be enough to save it. because while stellar winds reduce mass over time, gravity continues waiting patiently at the centre. Fusion can resist collapse only while fuel remains available. Once the core changes enough, once nuclear burning can no longer support the crushing weight above it, the entire balance fails. For ordinary stars like the Sun, that ending unfolds gradually across millions of years. For giant stars, the transition may happen astonishingly fast. And when stars as massive as R136a1 finally collapse, the resulting explosion may rank among the most energetic events in the universe. Human beings have a fascinating habit of asking catastrophic hypothetical questions right before bed. What if an asteroid hit Earth? What if the moon disappeared? What if a black hole entered the solar system? And eventually, somewhere along the line, someone inevitably asks what would happen if R136a1 replaced the Sun. The short answer is that it would solve most of humanity's long-term problems by very rapidly eliminating humanity. The longer answer is considerably more interesting, because replacing the Sun with R136a1 would not merely make Earth hotter. It would fundamentally transform the entire structure and behaviour of the solar system almost instantly. The scale of the star's radiation, luminosity, stellar winds and gravity would overwhelm nearly every familiar condition humans associate with planetary existence. And the truly unsettling part is this: many of the catastrophic effects would occur before the star even physically arrived. That's because stars influence their surroundings through radiation travelling at the speed of light. If R136a1 somehow replaced the Sun magically, Earth would continue orbiting normally for about 8 minutes before any visible changes occurred, because sunlight itself takes approximately 8 minutes to travel from the Sun to Earth. Those would be an unusually important 8 minutes. Birds would continue flying, cars would continue moving, people would continue checking phones while pretending not to, and then the first photons from R136a1 would arrive. At that moment, the solar system would effectively stop resembling the solar system. The brightness alone would become almost impossible to describe meaningfully. R136a1 shines with millions of times the luminosity of the Sun. Earth currently receives around 1,360 watts of solar energy per square metre at the top of the atmosphere. Replace the Sun with R136a1, and the incoming radiation would increase catastrophically. Temperatures would rise almost immediately. The atmosphere would begin heating rapidly. Oceans would start evaporating. Surface materials would struggle to remain chemically stable. And all of this would happen astonishingly fast, because the energy involved is so extreme. People often imagine planetary destruction as something dramatic but gradual, cities slowly burning beneath expanding heat. Reality would likely be far more abrupt and physically overwhelming. The atmosphere itself would become one of the first casualties. R136a1 emits enormous quantities of ultraviolet radiation, vastly more energetic than the sunlight Earth currently receives. Ultraviolet photons carry enough energy to strip electrons from atoms and molecules, a process called ionization. Earth's upper atmosphere already experiences ionization from solar radiation, but under R136a1's output, the process would intensify beyond anything remotely survivable. Molecules in the atmosphere would begin breaking apart rapidly. Ozone would disappear almost instantly. Nitrogen and oxygen chemistry would destabilize. The atmosphere would heat and expand dramatically. And because the radiation pressure is so intense, portions of the atmosphere could begin escaping into space entirely. This is not theoretical speculation in the abstract. Astronomers observe similar atmospheric stripping effects on planets orbiting extremely active stars elsewhere in the galaxy. Giant stars flood nearby space with radiation powerful enough to erode planetary atmospheres over time. R136a1 would simply perform the process with astonishing efficiency. And then there is the temperature problem. Earth currently maintains relatively stable temperatures because the Sun, despite being enormous, is actually a fairly moderate star. Its energy output sits comfortably within the range, allowing liquid water to exist on Earth's surface. R136a1 would obliterate that balance instantly. The oceans would begin boiling rapidly, not simmering politely, boiling catastrophically. Surface water would evaporate into the atmosphere, creating dense superheated steam layers. The greenhouse effect would spiral out of control almost immediately as trapped heat accumulated faster than the planet could radiate it away. Eventually, the oceans themselves would cease existing as stable bodies of liquid water, and after that, conditions would continue worsening. At sufficiently high temperatures, rocks themselves begin melting. The crust destabilizes, metals soften and vaporize, chemical structures break apart entirely. Earth would transition from habitable world to glowing planetary furnace in remarkably short order. And this still only addresses radiation and heat. We have not yet discussed the stellar wind. The Sun produces a solar wind that Earth's magnetic field mostly deflects successfully. Under ordinary conditions, Earth's magnetosphere protects the atmosphere and surface from much of the incoming charged particle radiation. R136a1's stellar wind would be vastly more powerful. Charged particles travelling thousands of kilometers per second would slam into Earth continuously. The magnetosphere would compress violently beneath the pressure. Radiation storms would intensify across the planet. Electronic systems would fail almost immediately. Power grids, satellites, communication networks, navigation systems, every technological structure dependent on stable electromagnetic conditions would collapse rapidly. Though admittedly civilization would already have larger concerns at that point. And there is another unsettling consequence many people forget. The sky itself would change completely. Earth currently experiences day and night because the Sun occupies a manageable brightness level relative to the atmosphere and planetary rotation. Under R136a1, daylight would become almost indescribably intense. The star's apparent size in the sky would also differ because R136a1 is physically larger than the Sun, though not proportionally as enormous as its luminosity increase. Still, the visible brightness would dominate the heavens overwhelmingly. Nighttime as humans understand it would effectively disappear. Even the far side of Earth would experience intense atmospheric scattering from the star's radiation. The sky itself could glow continuously due to ionized atmospheric gases. Stars would vanish from visibility entirely. The moon would reflect overwhelming amounts of light. Shadows might blur beneath scattered radiation flooding the atmosphere from every direction. The solar system would no longer feel peaceful or stable. It would resemble a region orbiting an active cosmic weapon. And perhaps the strangest detail is that Earth might not even remain in its current orbit. Now, purely from gravity alone, replacing the Sun with a much more massive star would alter planetary orbits dramatically. R136a1 contains vastly more mass than the Sun. Under normal circumstances, Earth's orbit would no longer remain stable at one astronomical unit. The stronger gravity would pull planets inward into different orbital dynamics entirely. However, because this hypothetical assumes Earth somehow remains in roughly its current orbital distance for the sake of discussion, the radiative effects already destroy habitability long before orbital mechanics become the dominant concern. Still, the rest of the solar system would change too. Mars would become hotter than present-day Earth. Jupiter's moons could warm dramatically. Outer planets would receive more energy than inner planets currently do under the Sun. The Kuiper belt would illuminate faintly. Even distant icy bodies near the edge of the solar system would begin absorbing enormous quantities of radiation compared to their normal frozen darkness. The entire solar system would transform into a violently illuminated environment. And all this assumes R136a1 remains stable, which is optimistic, because giant stars near the upper mass limit are unstable by nature. R136a1 continuously loses mass through powerful stellar winds. Radiation pressure nearly balances gravity. Internal turbulence churns through the star constantly. At some point the star will eventually die, and that ending matters enormously for nearby planets. The Sun will eventually become a red giant billions of years from now, expanding slowly and shedding outer layers relatively gently by cosmic standards. R136a1 will not die gently. Stars this massive may explode as hypernovae or collapse directly into black holes after catastrophic instability. Some may produce gamma-ray bursts, focused beams of radiation among the most energetic events in the universe. If Earth orbited nearby during such an event, the planet would not survive in any recognizable form. The explosion could outshine entire galaxies temporarily. Radiation would sterilize vast regions of surrounding space. Shock waves would sweep outward, carrying enormous kinetic energy. The supernova remnant itself might expand across light years, which means that even if Earth somehow survived the star's ordinary lifetime, the ending would almost certainly finish the job. There is another interesting consequence hidden inside this thought experiment though. R136a1 could never realistically exist in the Sun's place naturally. The conditions required to form giant stars differ enormously from those surrounding the Sun's birth. Massive stars emerge inside dense, crowded stellar nurseries like the Tarantula Nebula, where enormous quantities of gas collapse rapidly. The Sun formed in a comparatively moderate environment. That distinction matters because stable planetary systems and giant hypermassive stars may be somewhat incompatible long-term. Massive stars disrupt surrounding regions aggressively through radiation and stellar winds. Planet formation becomes difficult near such intense objects. In a strange way, the very reason Earth exists comfortably may be because the Sun is relatively ordinary. Humans sometimes underestimate how fortunate that ordinariness is. The Sun is stable, long-lived, predictable. Its energy output changes gradually enough for biological evolution to proceed across billions of years. A star like R136a1 burns too violently and dies too quickly to support similar evolutionary timescales nearby. Complex life requires patience from a star. R136a1 has no patience whatsoever, and perhaps that is one of the most fascinating lessons giant stars teach us. The universe permits astonishing extremes, but those extremes often come at the cost of stability. Giant stars shine brilliantly precisely because they consume themselves so rapidly. They dominate surrounding space, but only briefly. Smaller stars survive quietly for vastly longer. In fact, most stars in the universe are tiny red dwarfs that may continue burning long after giant stars like R136a1 have exploded and vanished completely. Spectacle and longevity rarely coexist in stellar physics. Still, giant stars remain profoundly important despite their instability. Their radiation shapes galaxies, their winds enrich nebulae, their deaths forge heavy elements necessary for planets and life. Without giant stars, the universe would look very different. Deep inside R136a1, the laws of physics begin behaving less like the calm, predictable rules we experience on Earth, and more like emergency systems struggling to maintain order under impossible conditions. That may sound exaggerated, but giant hypermassive stars genuinely push matter into regimes where ordinary intuition stops being useful almost immediately. The Sun already contains extreme physics. Its core pressure and temperature exceed anything humans can recreate naturally on Earth. Yet compared to R136a1, the Sun still operates within relatively stable and well-understood territory. R136a1 moves much closer to the edge. The pressures become larger, the radiation becomes more violent, the internal turbulence becomes more chaotic, and the balance between gravity and energy generation grows so delicate that even small changes inside the star can influence its entire future. One of the first strange things astronomers realized about hypermassive stars is that their interiors are dominated not just by ordinary gas pressure, but increasingly by radiation pressure. That distinction matters enormously. In everyday life, pressure usually comes from particles physically colliding with each other. Air molecules bounce around inside Earth's atmosphere. Gas atoms move inside engines or weather systems. Heat increases particle motion, which increases pressure. Ordinary stars work partly this way too, but inside extremely massive stars, light itself becomes one of the dominant sources of pressure. Photons generated through fusion carry momentum outward. In smaller stars, this contribution exists but remains secondary. In objects like R136a1, radiation pressure becomes overwhelming. The star is so luminous internally that light itself helps support the star against gravitational collapse. That is a deeply strange idea if you stop to think about it for more than a few seconds. A giant star survives partly because trillions upon trillions of photons continuously push outward from the core, with enough force to resist the crushing weight of hundreds of solar masses above them, and gravity pushes back constantly. This creates a highly unstable equilibrium. Smaller stars can remain relatively calm for billions of years because gas pressure and fusion rates settle into stable balance. Hypergiant stars live much closer to disaster. Radiation pressure nearly overwhelms gravity in some regions, especially near the surface. Astronomers describe this using the Eddington limit, the point where outward radiation pressure almost equals inward gravitational force. R136a1 exists frighteningly close to that boundary. And near the Eddington limit, strange things begin happening. The outer layers become unstable. Material escapes more easily. Small fluctuations in energy output can trigger enhanced mass loss. The star effectively struggles to hold itself together. This is one reason hypermassive stars lose enormous amounts of mass through stellar winds. Their radiation is simply too intense to remain fully contained. In some regions, light itself pushes matter outward strongly enough to launch plasma into surrounding space continuously. Another unusual feature inside giant stars involves convection. Convection occurs when hot material rises while cooler material sinks, similar to boiling water inside a pot. The Sun contains convective regions too, but in hypermassive stars the process becomes much more extensive and turbulent. Inside R136a1, enormous convection currents likely churn through large portions of the star. Hot plasma rises, cooler material sinks inward. Fusion products get transported throughout the interior far more efficiently than in smaller stars. This internal mixing changes stellar evolution dramatically. In ordinary stars, the core and outer layers remain somewhat distinct chemically. Fusion products accumulate gradually near the center, while outer layers stay relatively untouched. Hypergiant stars mix themselves much more aggressively. Fresh hydrogen can circulate inward. Helium and heavier elements move outward. The star behaves more like a gigantic turbulent engine than a neatly layered sphere. That mixing allows giant stars to burn fuel differently, and sometimes longer than simpler models originally predicted, at least longer relative to how violently they consume energy. Still, longer remains an extremely generous term in this context because R136a1 may only survive a few million years total, which is astonishingly short for a star. One especially bizarre consequence of these conditions is that the star may become chemically almost uniform throughout large regions. Instead of developing sharply separated internal layers early on, rotational mixing and convection can distribute material more evenly. The star effectively stirs itself, and rotation matters too. Massive stars often spin rapidly. Rotation changes internal pressure distributions, influences convection, and affects how material moves throughout the star. Fast rotation can flatten the star slightly near the poles and alter how radiation escapes from different regions. Some massive stars even rotate fast enough to approach breakup speed, where centrifugal forces begin competing significantly against gravity. R136a1 may not rotate quite that extremely now, partly because stellar winds remove angular momentum over time, but rotation still influences its structure and evolution. The more scientists study giant stars, the less they resemble simple glowing balls of gas. Instead, they become astonishingly dynamic systems governed by competing instabilities. Radiation pressure pushes outward, gravity crushes inward, convection churns material constantly, rotation reshapes internal flows, stellar winds remove mass continuously, fusion rates evolve rapidly. Every process affects every other process simultaneously, and perhaps most remarkably, all of this occurs while temperatures and densities remain so extreme that matter itself behaves differently than under ordinary conditions. The core of R136a1 reaches tens of millions of degrees. At those temperatures, atoms cannot survive intact. Electrons separate completely from nuclei, creating plasma. Nuclear reactions proceed continuously. High-energy photons dominate the environment. The densities also become extraordinary. Imagine compressing enormous quantities of matter beneath hundreds of solar masses of pressure. The core experiences conditions difficult for human minds to visualize meaningfully, because nothing remotely comparable exists naturally on Earth. Even laboratory fusion experiments only approximate tiny fragments of such environments for extremely brief moments, and yet giant stars maintain these conditions for millions of years. One fascinating consequence involves energy transport. Inside the Sun, photons generated in the core may require hundreds of thousands or even millions of years to escape, because they scatter repeatedly through dense matter. In R136a1, energy transport becomes even more complicated. Radiation pressure dominates large regions. Convection carries energy through turbulent flows. Dense plasma continuously absorbs and re-emits photons. The star glows brilliantly on the outside, but internally the movement of energy resembles a chaotic traffic system operating under catastrophic pressure. Another strange feature appears near the surface. Ordinary stars possess reasonably defined outer layers. Hypergiant stars become harder to define precisely because their atmospheres merge gradually into powerful outflowing winds. Where exactly does the star end and the stellar wind begin? The answer becomes surprisingly unclear. R136a1 continuously ejects matter outward at enormous speeds. The atmosphere expands and thins gradually into surrounding space. Radiation accelerates material away constantly. In some ways, the star behaves less like a stable object and more like a continuous eruption held together temporarily by gravity. And because the star is so luminous, even tiny opacity changes inside the atmosphere can trigger instabilities. Opacity measures how easily radiation passes through material. Certain elements absorb light more effectively at specific temperatures and ionization states. In giant stars, these effects can create layers where radiation suddenly pushes harder against surrounding matter. The result can be pulsations or enhanced mass loss episodes. The star breathes unevenly, not rhythmically like a heartbeat, but dynamically, constantly adjusting under competing pressures. There are also theoretical questions about pair instability inside extremely massive stars. At sufficiently high temperatures, energetic gamma-ray photons inside the core can spontaneously convert into electron-positron pairs, gamma going to E- plus E+. This process sounds almost like science fiction, but it follows ordinary particle physics under extreme conditions. The problem is that gamma rays normally contribute important radiation pressure supporting the star against gravity. When photons transform into particles instead, pressure suddenly drops. Gravity gains temporary advantage. The core contracts rapidly. Temperatures rise even further. Fusion reactions accelerate explosively. For certain mass ranges, this can trigger catastrophic instability, called a pair instability supernova, an explosion so powerful that the entire star may be completely destroyed without leaving behind a black hole. Astronomers still debate whether R136a1 might eventually experience something similar, or whether mass loss through stellar winds will reduce the star enough to avoid full pair instability before final collapse. That uncertainty reveals how difficult giant stellar physics remains even today. Scientists understand the broad principles well, but precise outcomes become complicated because so many interacting processes influence evolution simultaneously. And the larger the star becomes, the harder the calculations get. Computer simulations of hypermassive stars require enormous complexity. Radiation transport, magnetic fields, rotation, convection, turbulence, nuclear reactions, stellar winds, and relativistic effects all interact continuously. Tiny differences in assumptions can alter long-term outcomes dramatically. Even defining the exact mass of R136a1 becomes challenging, because strong winds and extended atmospheres blur observational boundaries. Yet despite these difficulties, one thing remains clear. Stars like R136a1 occupy an entirely different physical regime from ordinary stars. They push matter and energy near the limits of stable stellar existence. And strangely enough, the universe may once have produced even larger stars regularly. Shortly after the Big Bang, the first generations of stars likely formed under very different conditions. Heavy elements barely existed. Gas cooled differently. Fragmentation processes changed. Astronomers suspect primordial stars may have reached enormous masses routinely, perhaps even exceeding modern giants like R136a1. Those first stars would have transformed the early universe dramatically through radiation, fusion, and explosive deaths. In some ways, R136a1 may represent a surviving glimpse of that older cosmic era, a modern example of physics once more common in the young universe. And yet despite all this complexity, despite all the equations and simulations and spectral analysis, there remains something emotionally strange about giant stars. They are temporary, violently temporary. R136a1 contains enough matter to build hundreds of solar systems, radiates with unimaginable power, reshapes surrounding nebulae, and pushes physics toward instability, yet it may survive only a few million years before collapsing. That imbalance between scale and lifespan feels almost unfair. Smaller stars endure quietly for trillions of years. The giants burn brilliantly and vanish early. But perhaps that brief intensity is exactly what makes them important. Because hypermassive stars do not simply exist. They transform everything around them while they live. And eventually, when the balance inside finally fails completely, the ending may become one of the most violent events the universe can produce. Which raises another fascinating question. If stars like R136a1 are so unstable today, what must conditions have looked like in the early universe, when giant stars may have been even more common? Roughly 13.8 billion years ago, the universe was a remarkably simple place. Not simple in the sense of being calm or gentle. The early universe was unimaginably hot, dense, and violent. But chemically it lacked almost everything familiar to modern astronomy. No rocky planets existed, no carbon-rich worlds, no oxygen atmospheres, no iron cores, no trees, no oceans, no living organisms wondering why giant stars insist on behaving so recklessly. There was mostly hydrogen, some helium, tiny traces of lithium, and not much else. Every heavier element in existence today, every atom of carbon in your body, every oxygen atom you breathe, every calcium atom inside your bones had yet to be created. That work would fall largely to stars, and in the beginning, the universe may have specialized in building truly enormous ones. Modern giant stars like R136a1 already push the boundaries of what stellar physics comfortably allows. Yet many astronomers suspect the earliest stars in cosmic history may have been even larger, possibly much larger. To understand why, we need to imagine a universe before chemistry became complicated. Today, star-forming clouds contain heavy elements produced by earlier generations of stars. Astronomers refer to these heavier elements collectively as metals, which sounds slightly confusing because in astronomy, Oxygen and carbon count as metals while actual human metals merely look offended in the background. These heavy elements matter enormously because they help gas clouds cool. Cooling is essential during star formation. As gas collapses inward under gravity, it heats up. If the cloud cannot cool efficiently, pressure builds and resists further collapse. Heavy elements and dust radiate heat away effectively, allowing modern molecular clouds to fragment into many smaller regions. That fragmentation produces large numbers of relatively modest stars. The early universe lacked those heavy elements. Primordial gas clouds cooled less efficiently. Without effective cooling, collapsing regions may have remained much larger before fragmentation occurred. Instead of forming countless smaller stars, enormous clouds could continue collapsing into giant protostars. The result may have been the first generation of stars known as population 3 stars. Astronomers have never directly observed one. That detail is important. Population 3 stars remain theoretical because the earlier stars likely lived fast and died young. By the time the universe became transparent enough and evolved enough for galaxies to form visibly, those first stars had probably already exploded or collapsed. Still, simulations strongly suggest they existed, and they may have been monsters. Some models estimate population 3 stars reached masses of several hundred solar masses. Certain calculations even allow masses approaching 1,000 solar masses under specific conditions. Imagine something larger than R136a1 burning inside a universe still almost chemically empty. A giant blue-white furnace illuminating primordial darkness for the first time. That image is one of the most extraordinary in all of cosmology. Before stars existed, the universe entered a period sometimes called the Cosmic Dark Ages. After the Big Bang cooled enough for neutral hydrogen atoms to form, space became largely dark and featureless. Matter drifted through expanding space quietly. Gravity slowly amplified tiny density variations left behind from the early universe. Then eventually, somewhere inside collapsing clouds of primordial gas, the first stars ignited, and the universe changed forever. These giant early stars probably looked very different from the Sun, hotter, larger, more unstable. Their intense ultraviolet radiation flooded surrounding space immediately. One of their most important effects involved reionization. Neutral hydrogen dominated the young universe initially, but giant stars emitted enormous quantities of high-energy radiation capable of stripping electrons away from hydrogen atoms again. Gradually, regions around early stars became ionized. Over time, more stars formed, more radiation spread outward. Eventually, much of the universe transitioned from neutral gas into ionized plasma once again. Astronomers call this process cosmic reionization, and giant primordial stars likely played a major role in driving it. In a sense, the first giant stars turned the lights back on, and they did so violently, because massive stars never live quietly. Population 3 stars probably burn through fuel with astonishing speed. Many may have survived only a few million years before collapsing or exploding. Their enormous masses created crushing core pressures and extreme fusion rates, just like R136a1, but perhaps even more dramatic. And because the early universe lacked heavy elements, stellar winds may have behaved differently too. Modern massive stars lose huge amounts of mass through radiation-driven winds, partly because heavy elements in their atmospheres absorb photons efficiently. Lower metallicity stars may experience weaker winds. That means primordial stars could potentially retain more of their original mass throughout their lives, which in turn affects how they die. Some may have undergone pair instability supernova, explosions so powerful that the entire star gets completely disrupted. Others may have collapsed directly into black holes, and those black holes could become extremely important later. One of the great mysteries in astronomy involves supermassive black holes. These enormous objects sit at the centers of most galaxies, including the Milky Way. Some formed astonishingly early in cosmic history, less than 1 billion years after the Big Bang. That creates a timing problem. How did black holes grow so massive so quickly? One possibility is that giant primordial stars provided unusually massive seed black holes early on. If population 3 stars routinely reached hundreds of solar masses before collapsing, they could create relatively large black holes immediately. Those black holes might then grow further by accreting gas and merging with others. In this way, the brief lives of early giant stars may have helped shape the architecture of galaxies themselves. The universe appears remarkably dependent on temporary extremes, and perhaps nowhere is that clearer than in stellar chemistry. Remember, the early universe contained almost no heavy elements. Giant stars changed that permanently. Inside their cores, nuclear fusion forged progressively heavier atoms. Hydrogen became helium. Helium fused into carbon and oxygen. Larger stars continued building even heavier nuclei through successive fusion stages. Eventually, supernova explosions scattered those elements into surrounding space. For the first time, the universe became chemically enriched. Later generations of stars formed from this recycled material. Planets became possible. Rocky surfaces emerged. Complex chemistry evolved. Life eventually appeared. Everything familiar today depends on those ancient stars altering the composition of the cosmos itself. Without them, the universe might remain mostly hydrogen forever. There is something strangely comforting about that. Every atom heavier than helium in your body once passed through stellar interiors long before Earth existed. The calcium in your teeth, the iron in your blood, the oxygen filling your lungs, all originated from nuclear processes inside stars. You're quite literally assembled from ancient stellar debris, and giant stars accelerated that process enormously because they evolved so rapidly. A small red dwarf star may survive for trillions of years while contributing relatively little to cosmic chemical evolution. Giant stars live briefly but dramatically. They flood galaxies with radiation and heavy elements quickly. The universe seems to rely on both approaches simultaneously. Quiet, long-lived stars for endurance, massive unstable stars for transformation. Another fascinating aspect of primordial stars involves visibility. Modern astronomy relies heavily on observing light from distant objects, but the earlier stars remain extraordinarily difficult to detect directly because they existed so long ago and so briefly. Their light stretched enormously due to cosmic expansion. Their lifetimes were short. Many formed inside dense regions difficult to observe clearly. Still, astronomers continue searching for indirect evidence. The James Webb Space Telescope has already begun revealing galaxies from astonishingly early periods of cosmic history. Some observations hint at unexpectedly rapid star formation and large stellar populations very early in the universe. Researchers hope future observations may eventually uncover clear evidence of population 3 stars or their immediate descendants. Even if individual primordial stars remain invisible, their fingerprints may survive in ancient gas clouds or unusual stellar populations. Astronomy often works like cosmic archaeology. Scientists reconstruct vanished objects through indirect clues left behind across billions of years, and giant stars leave dramatic clues: supernova remnants, chemical enrichment patterns, black hole populations, radiation signatures. The early universe may have looked radically different from today, partly because giant stars dominated so strongly. Imagine galaxies filled with enormous blue-white stars burning intensely amid chemically primitive gas clouds, radiation flooding through young space, supernova explosions occurring frequently, black holes forming rapidly. The cosmos would feel far harsher and more unstable than the relatively mature universe surrounding modern Earth. Yet without that instability, later cosmic structure might never emerge, and that creates an interesting connection back to R136a1. Inside the Tarantula Nebula, astronomers observe conditions resembling miniature echoes of those ancient times: dense star formation, giant unstable stars, lower metallicity environments than much of the Milky Way. R136a1 may not be a true primordial star, but it helps scientists study physics similar to what governed the first stellar generations. In many ways, giant stars act like bridges between cosmic eras. They connect the modern universe to its violent beginnings, and they remind us how temporary stability really is on large scales. Earth exists during an unusually calm period around a relatively stable star. The early universe likely offered far fewer peaceful neighborhoods. Radiation levels ran higher. Massive stars exploded frequently. Galaxies evolved rapidly. Cosmic childhood was not especially gentle. Still, it was productive. The universe transformed chemically, structurally, and dynamically during those first stellar generations. Giant stars drove much of that change precisely because they burned so fast and died so violently. There is an almost paradoxical beauty in that. The shortest-lived stars often leave the deepest marks on cosmic history. And eventually, every giant star faces the same unavoidable problem. Fusion cannot continue forever. The core changes. Pressure balance fails. Gravity begins reclaiming control. For primordial giants, those endings may have created the first black holes and the first truly massive explosions in cosmic history. For R136a1, the ending still lies somewhere in the future. Nothing in the universe lasts forever, but giant stars seem especially aware of the arrangement. From the moment a hypermassive star like R136a1 ignites, its ending is already approaching unusually fast. The star burns through nuclear fuel with astonishing intensity, continuously losing mass through violent stellar winds while balancing precariously against gravity, and eventually gravity wins. The truly difficult question is not whether R136a1 will die. It is how. Because stars this massive exist in a strange region of stellar physics where several different catastrophic endings become possible. Astronomers can model the possibilities, compare observations and run simulations, but nature still retains a frustrating habit of surprising everyone at the exact moment scientists begin feeling confident. Still, we understand the broad outline reasonably well, and the broad outline is spectacularly violent. The first thing to remember is that stars survive only because fusion pushes outward against gravitational collapse. As long as nuclear reactions continue in the core, energy flows outward and maintains pressure strong enough to resist the enormous weight of the star pressing inward. Fusion is life for a star. When fusion fails, stability fails with it. For smaller stars like the Sun, this process unfolds relatively gradually. Billions of years from now, the Sun will expand into a red giant, shed outer layers, and eventually leave behind a white dwarf surrounded by a glowing planetary nebula. The Sun's death will be dramatic by human standards, but comparatively gentle by cosmic ones. R136a1 will not die gently. Massive stars experience a very different evolutionary path because their cores become hot enough to fuse progressively heavier elements. Hydrogen becomes helium, helium becomes carbon and oxygen. Larger nuclei form under increasing pressure and temperature. Each fusion stage generates energy for a shorter time than the last. Hydrogen fusion may last millions of years. Helium fusion proceeds more quickly. Carbon burning accelerates further. Near the end, silicon fusion can occur astonishingly fast. And eventually the star reaches iron. Iron is a problem. Fusion releases energy only while combining lighter elements into heavier ones up to iron. Beyond iron, fusion no longer produces net energy. Instead, it consumes energy. That means once a giant star builds a substantial iron core, the process supporting the star against gravity effectively stops working. The core can no longer generate enough outward pressure through fusion. Gravity suddenly gains the advantage, and when collapse begins inside a star this massive, it happens with terrifying speed. The core implodes catastrophically in less than a second. Matter falls inward at enormous velocities. Temperatures soar, densities rise beyond ordinary comprehension. Electrons and protons may combine into neutrons. Shockwaves form deep inside the collapsing star. The entire structure destabilizes almost instantly. For many massive stars, this collapse triggers a core collapse supernova. The imploding core rebounds violently, generating an explosion capable of briefly outshining entire galaxies. Outer layers blast outward into space, carrying enormous kinetic energy and freshly forged heavy elements. Supernovae are among the most powerful explosions in the universe, but R136a1 may exceed even ordinary supernova territory. Because stars this massive introduce additional possibilities. One candidate ending is a hypernova. Hypernovae are essentially extremely energetic supernovae associated with exceptionally massive stars. They may release many times more energy than ordinary core collapse events and can produce gamma-ray bursts under certain conditions. A gamma-ray burst deserves a moment of appreciation because it represents one of the most violent known phenomena in existence. During some stellar collapses, narrow jets of ultra-energetic radiation blast outward near the speed of light. If one of these jets happens to point toward Earth from nearby cosmic distances, the consequences could be catastrophic for planetary atmospheres and biological systems. Fortunately, R136a1 resides safely inside the Large Magellanic Cloud, around 160,000 light-years away, which gives humanity a reassuring amount of distance from any future stellar tantrums. Still, the sheer energy involved remains astonishing. A hypernova can release more energy in seconds than the Sun will emit during its entire lifetime. That sentence sounds exaggerated every time. It remains true. And yet even hypernovae may not fully describe what happens to stars near the upper mass limit. There is another strange possibility called pair instability. We touched on this earlier, but now the consequences become important. Inside extremely massive stars, core temperatures can become so intense that high-energy gamma-ray photons spontaneously transform into electron-positron pairs, gamma going to E- plus E+. Normally, radiation pressure from gamma rays helps support the star against gravity, but when photons convert into particles instead, radiation pressure suddenly drops. The core loses support, gravity accelerates collapse, temperatures rise even more dramatically, fusion reactions ignite explosively, and the result may become a pair instability supernova. Unlike ordinary supernova, which often leave behind neutron stars or black holes, pair instability supernova can completely destroy the entire star. Nothing remains, no stellar remnant, no collapsed core. The explosion disperses the entire object into space. Imagine a star hundreds of times more massive than the Sun simply detonating so completely that it ceases existing altogether. That possibility is one reason astronomers remain fascinated by R136a1. Its mass places it near the regime where pair instability effects may matter. But there is a complication. R136a1 loses enormous amounts of mass through stellar winds during its lifetime. Those winds may reduce the star enough before collapse to prevent full pair instability from occurring, and this is where the uncertainty begins. Astronomers still debate exactly how stars like R136a1 evolve because small differences in mass loss rates can dramatically alter the ending. If the star retains enough mass, pair instability may dominate. If winds strip too much material away, the star may instead undergo ordinary core collapse or direct black hole formation. Some models even suggest the star could collapse almost directly into a black hole, with relatively little visible explosion at all. That possibility feels strangely anticlimactic after spending millions of years behaving like one of the brightest objects in the universe. Imagine a giant stellar furnace radiating with unimaginable intensity, only to disappear inward suddenly beneath gravity. Yet nature permits exactly such outcomes. And black hole formation itself becomes extraordinary at these masses. The collapse of a giant stellar core compresses matter beyond neutron star densities. Gravity overwhelms every known pressure support mechanism. Space-time curves inward catastrophically. Eventually an event horizon forms. A black hole is born. If R136a1 eventually collapses into a black hole, the resulting object could become quite massive, especially if enough material survives collapse rather than escaping during explosion. And that connects giant stars directly to one of the biggest mysteries in modern astronomy. Where do intermediate and supermassive black holes come from? Stars like R136a1 may provide part of the answer. Massive stellar collapses in the early universe could create unusually large black hole seeds. Those seeds might later merge and accrete matter, eventually growing into the supermassive black holes found at the centers of galaxies today. In that sense, giant stars may help build some of the largest structures in the observable universe through their deaths. The universe is remarkably efficient at turning endings into beginnings. Another fascinating aspect of giant stellar death involves nucleosynthesis. During collapse and explosion, enormous temperatures and pressures create conditions capable of forging heavy elements rapidly through neutron capture processes. Gold, uranium, rare heavy nuclei. Some of the rarest elements on Earth formed during catastrophic stellar deaths long before the solar system existed. That means jewelry, nuclear reactors, and certain geological materials owe their existence partly to exploding stars. Cosmic violence leaves surprisingly decorative leftovers sometimes. R136a1's eventual explosion, whatever form it takes, will enrich surrounding space further. Heavy elements forged during its life and death will scatter through the surrounding nebula. Future generations of stars and planets may eventually form from that material. Perhaps somewhere billions of years from now, life may emerge partly from atoms once buried inside R136a1's core. That idea never stops feeling slightly surreal. And yet the timeline involved is astonishingly brief compared to smaller stars. The Sun may survive for roughly 10 billion years. R136a1 may last only a few million. A cosmic firework compared to a steady lantern. There is something oddly emotional about that contrast, even though stars themselves feel nothing. Giant stars achieve extraordinary brilliance precisely because they sacrifice longevity. Their lives are unstable, wasteful, violent, and transformational. The universe allows spectacular excess, but only temporarily. One especially haunting thought involves visibility. If R136a1 exploded tomorrow, humanity would not know immediately because the star lies about 160,000 light-years away. Any explosion occurring there now would already have happened long ago from Earth's perspective. We observe the star as it existed 160,000 years in the past. In fact, the real R136a1 might already be dead. That possibility applies to all distant astronomy eventually. Telescopes always observe history. Light takes time to travel. The farther away an object lies, the older the information we receive. When astronomers study distant galaxies, they literally observe ancient cosmic epochs. So somewhere inside the Large Magellanic Cloud, R136a1 may currently still blaze with impossible brightness. Or perhaps the star already collapsed thousands of years ago, and the light simply has not arrived yet. There is no way to know immediately. That uncertainty gives astronomy a strangely reflective quality sometimes. The night sky looks stable, but many visible objects may no longer exist in the form we currently observe. Light preserves ghosts of earlier cosmic moments, and eventually, one day in Earth's future, telescopes may detect the death of R136a1 itself. A sudden explosion, a dramatic brightening, shockwaves expanding into surrounding space. Astronomers across the world would study every detail intensely because stars this massive remain rare. The event would help answer long-standing questions about giant stellar evolution, pair instability, black hole formation, and hypernova physics. And afterward, whatever remains of the star would continue influencing surrounding space, because giant stars rarely disappear quietly. Their deaths reshape nebulae, enrich galaxies, and sometimes create objects even stranger than the stars themselves. Far beyond the comfortable scale of everyday human experience, the universe appears strangely willing to reward excess, build a mountain, and erosion eventually wears it down. Build a civilization, and time slowly reshapes it. Build a star hundreds of times more massive than the Sun, and the cosmos responds with black holes, gamma-ray bursts, and explosions bright enough to briefly outshine entire galaxies. Giant stars rarely leave small consequences behind, and when something like R136a1 finally dies, its influence may continue long after the star itself disappears. One possible ending involves black hole formation. Black holes already sound dramatic enough before you remember they are real physical objects scattered throughout the universe in enormous numbers. They are not holes in the ordinary sense, but regions where gravity becomes so intense that escape velocities exceed the speed of light. Once matter crosses the event horizon, no information returns outward, at least according to current physics, and giant stars provide one of the main pathways for creating them. When a sufficiently massive stellar core collapses after fusion fails, gravity overwhelms every known pressure support mechanism. Electrons cannot resist. Neutrons may briefly resist. But eventually, if enough mass remains concentrated in a small enough region, collapse continues beyond even neutron star stability. Space-time itself curves catastrophically inward. An event horizon forms. A black hole is born. For ordinary stellar black holes, masses often range from several to perhaps a few dozen times the mass of the Sun. But giant stars like R136a1 may create more substantial remnants under the right conditions, especially if the star collapses directly rather than ejecting most of its mass during explosion. That distinction matters. Some supernovae blast enormous amounts of material outward before the remaining core collapses. Others may undergo fallback, where ejected matter falls inward again afterward. And some extremely massive stars may collapse so efficiently that much of the star disappears directly into the forming black hole. Astronomers sometimes describe this as a failed supernova, though from a human perspective the process still sounds alarmingly successful at destroying stars. One moment a giant stellar furnace dominates its region of space. The next moment much of that mass vanishes behind an event horizon. And because black holes themselves emit no light directly, the visible star may simply disappear suddenly. There is something strangely unsettling about that possibility. A star millions of times brighter than the Sun, ending not with a spectacular explosion, but with darkness. Of course, the surrounding environment rarely remains quiet for long. Matter falling toward a newborn black hole heats intensely through friction and compression. Magnetic fields twist violently. Radiation floods outward from accretion disks. Jets may emerge from the poles at relativistic speeds, which brings us to gamma-ray bursts. These events rank among the most energetic phenomena known anywhere in existence. Gamma rays represent the highest energy form of electromagnetic radiation. Human bodies evolve beneath visible sunlight and relatively gentle cosmic conditions. Gamma rays belong to a far more dangerous category entirely. They penetrate matter deeply, disrupt molecular structures, and carry enormous amounts of energy. During certain stellar collapses, especially involving rapidly rotating massive stars, narrow jets of gamma radiation can blast outward near the speed of light. For a few seconds or minutes, those jets may release more energy than the Sun will emit during its entire lifetime. Again, that sentence sounds impossible every time. Again, it remains true. The important detail is that gamma-ray bursts are highly directional. The energy focuses into narrow beams rather than spreading equally in all directions. That means observers aligned with the jet experience extraordinary brightness, while other directions receive far less radiation. If Earth happened to lie close enough to a nearby gamma-ray burst aimed directly at us, the consequences could be severe. Atmospheric chemistry would suffer major disruption. Ozone depletion could occur. Surface radiation levels would increase dramatically. Some scientists have even explored whether ancient gamma-ray bursts might have contributed to certain extinction events in Earth's distant past, though the evidence remains uncertain. Fortunately, R136a1 lies safely inside the Large Magellanic Cloud, about 160,000 light-years away. That distance provides a very comforting amount of separation from any future stellar unpleasantness. Still, gamma-ray bursts help reveal just how extreme giant stellar deaths can become, and they may have played important roles throughout cosmic history. In the early universe, gamma-ray bursts from massive stars could influence surrounding gas clouds across enormous distances. Radiation from these events may alter star formation, ionize material, or reshape chemical environments inside young galaxies. Massive stars do not merely live dramatically, they alter cosmic evolution through their deaths, and black holes themselves continue influencing galaxies long afterward. A black hole formed from a giant star may accrete surrounding matter gradually over time. Gas falling inward heats intensely and radiates enormous energy before crossing the event horizon. If enough material accumulates, the black hole grows. Multiple black holes may merge. Clusters evolve. Galactic centers collect matter. Eventually, over cosmic timescales, some black holes become truly enormous. The Milky Way contains a supermassive black hole called Sagittarius, a star with millions of solar masses. Other galaxies contain black holes billions of times more massive than the Sun. And astronomers still debate exactly how these giants formed so quickly in the early universe. One possible answer involves stars larger than R136a1, which leads naturally to another fascinating question. Could even bigger stars exist somewhere in the universe? The honest answer is probably yes, at least temporarily. R136a1 currently holds the title of the most massive known star with reasonable observational confidence, but known matters enormously there. The observable universe contains hundreds of billions of galaxies, each containing billions of stars. Humanity has studied only a tiny fraction of them in detail. Somewhere out there, conditions may permit stars even larger than R136a1 to form briefly before instability destroys them. Dense stellar nurseries, low metallicity environments, crowded young clusters, unusual merger events. Nature has many opportunities to experiment, and stellar mergers may prove especially important. Inside dense clusters, giant stars can collide or merge under certain conditions. Imagine two already massive stars spiraling together and combining into something temporarily larger than either one alone. The resulting object may become highly unstable, rapidly rotating, and extraordinarily luminous. Some astronomers suspect certain giant stars observed today may actually represent merger products rather than single straightforward formation events. The universe, as usual, appears comfortable improvising. There are also theoretical ideas involving supermassive primordial stars in the early universe. Under special conditions shortly after the Big Bang, enormous gas clouds might collapse into giant stars thousands or even tens of thousands of solar masses large, before directly collapsing into black holes. These hypothetical objects could help explain the rapid appearance of supermassive black holes early in cosmic history. Imagine stars so enormous that R136a1 itself would seem moderate by comparison. The mind resists scales like that naturally, and perhaps that resistance is reasonable because physics itself begins struggling too. At sufficiently high masses, instability becomes difficult to avoid. Radiation pressure grows overwhelming, stellar winds intensify. Pair instability may trigger catastrophic collapse or explosion. Nature seems willing to construct giant stars, but only briefly and under very specific conditions. There may be practical upper limits imposed by stellar physics, or perhaps only temporary limits. Astronomy repeatedly teaches the same lesson. Whenever humans begin feeling certain about cosmic boundaries, the universe quietly reveals something stranger. For centuries, people assumed the Milky Way was the entire universe. Then other galaxies appeared. Astronomers believed planets outside the solar system might be rare. Now thousands are known. Scientists once thought stars above roughly 150 solar masses should barely exist. Then R136a1 arrived. It would therefore feel slightly unwise to declare confidently that no larger stars exist anywhere. The universe has earned some skepticism, and even if larger stars do exist, they likely remain exceptionally short-lived. That is the important trade-off underlying giant stellar evolution. The larger the star, the more unstable the balance becomes. More mass means stronger gravity. Stronger gravity means hotter fusion. Hotter fusion means greater luminosity. Greater luminosity drives stronger stellar winds and instability. Eventually the star destroys itself through either radiation, explosion, collapse, or some combination of all three. Gigantic stars live like cosmic fireworks, brief, violent, transformative, yet despite their short lifespans, giant stars leave enormous legacies behind. Their radiation shapes nebulae, their winds enrich galaxies, their deaths forge heavy elements, their collapses create black holes. Future stars and planets emerge partly from their remains. Even the atoms inside your body owe something to ancient generations of giant stars long vanished. That connection makes astronomy feel strangely intimate sometimes. The universe can appear overwhelmingly large and indifferent. Yet the material composing human beings passed through stellar interiors billions of years ago. You're physically connected to ancient cosmic events, whether you think about them often or not. Every breath contains atoms forged in stars. Every heartbeat depends on elements produced by stellar explosions. And somewhere inside the Large Magellanic Cloud, R136a1 currently continues its brief furious existence, radiating unimaginable energy while slowly dismantling itself through stellar winds. One day the balance will fail. Gravity will reclaim the core. The star may explode, collapse, or vanish into darkness behind an event horizon, but even afterward, its influence will continue spreading outward through space and time, because giant stars never really disappear completely. They become part of whatever comes next. And perhaps that is the most remarkable thing about the universe. Its most violent events are often also its most creative ones. Somewhere tonight, beyond the familiar stars above Earth, far outside the calm little neighborhood of our solar system, R136a1 continues burning inside the Tarantula Nebula, an object hundreds of times more massive than the Sun, a star so luminous that its radiation actively strips away its own outer layers, a stellar furnace balanced near the edge of physical stability. And somehow, despite everything we have explored tonight, despite the impossible temperatures, the violent stellar winds, the unstable physics, and the terrifying scale of its future death, perhaps the strangest thing about R136a1 is simply that it exists at all, because nature did not need to build a star like this. The universe could have settled for smaller stars, safer stars, long-lived stable objects quietly converting hydrogen into helium over trillions of years. In fact, most stars in existence behave exactly that way. Tiny red dwarfs dominate the cosmos numerically. Calm, efficient, durable. Yet every so often, gravity gathers enough material under the right conditions and produces something excessive, something reckless, something operating near the upper limits of what physics will temporarily allow, and the result is a giant star like R136a1. There is something almost unsettling about that willingness toward extremes. The universe does not merely permit enormous unstable stars. Under certain conditions, it seems remarkably eager to create them. Dense stellar nurseries collapse. Radiation floods outward. Matter compresses beneath gravity, fusion ignites, and suddenly a giant blue-white hypermassive star begins burning through its existence at astonishing speed. All for a lifespan that may last only a few million years. Cosmically speaking, that is almost nothing. The Sun will survive for roughly 10 billion years. Some red dwarf stars may continue glowing for trillions. R136a1 exists only briefly by comparison. A flash, a violent temporary imbalance, and yet during that short lifespan, the star reshapes enormous regions of space around it. Its radiation ionizes surrounding gas clouds, its stellar winds sculpt the nebula, its future collapse may create a black hole or hypernova. Heavy elements forged inside its core will eventually scatter into surrounding space and become part of future stars, planets, and perhaps living organisms. In other words, giant stars help build the future precisely because they destroy themselves so dramatically. The universe seems strangely dependent on temporary catastrophes. Without giant stars, galaxies would evolve differently. Chemical enrichment would slow. Rocky planets might remain rare. Complex biology might never emerge at all. Even the atoms inside your body owe their existence partly to generations of stars that lived violently and died explosively long before Earth formed. That idea never really loses its impact. Every person listening tonight carries material forged inside ancient stellar interiors, the calcium in your bones, the oxygen you breathe, the iron moving through your blood. Much of it originated in stars, some perhaps not entirely unlike R136a1. Astronomy often feels distant at first because the scales involved are so overwhelming. Light years, nebulae, black holes, galaxies. Numbers so large they stop feeling emotionally real. But eventually the subject becomes strangely personal, not because the universe was designed for us. There is no evidence of that. Giant stars are not compassionate objects. They are in different furnaces governed by gravity, fusion, radiation, and collapse. Yet we are physically connected to them anyway. Human beings emerge from a universe shaped by stellar evolution. The cosmos became chemically rich enough for biology only because earlier stars transformed it first, and giant stars accelerated that process enormously. In some ways, the universe needed monsters. That may be one reason objects like R136a1 feel so fascinating emotionally. They represent cosmic excess pushed almost beyond stability. A star too massive to live long, too luminous to remain calm, too energetic to quietly coexist with its surroundings. R136a1 does not merely shine, it overwhelms. And perhaps there is something strangely comforting about that too. Not the destructive part, certainly. Nobody wants a hypermassive Wolf-Rayet star relocating into the solar system unexpectedly. That would create several planning difficulties, but the existence of giant stars reminds us that the universe remains larger, stranger, and more dynamic than ordinary daily life sometimes allows us to remember. Here on Earth, human concerns can feel enormous. Deadlines, bills, unanswered messages. The awkward memory of something embarrassing said years ago that the brain still insists on replaying at 2 a.m. for absolutely no useful reason. Then astronomy quietly expands the scale. Beyond Earth lies the solar system. Beyond the solar system lies the galaxy. Beyond the galaxy lie billions more galaxies, and scattered among them are stars so extreme that they barely seem physically reasonable. Objects like R136a1 restore perspective through scale. Not because human life becomes meaningless beside the cosmos, but because the universe is large enough to contain both giant stars and small human moments simultaneously. A hypermassive star can burn inside a neighbouring galaxy, while somewhere else a person sits quietly listening to rain against a window after a long day. Both things exist at once, and perhaps that balance matters. Science sometimes gets portrayed as cold or purely mechanical, yet astronomy often produces the opposite feeling. The more we understand the universe, the more extraordinary it becomes. Giant stars are not less beautiful once explained. If anything, The explanations make them stranger. A star supported partly by radiation pressure, fusion running so intensely that the star strips away its own atmosphere, gamma rays transforming into matter inside collapsing cores, black holes forming from failed equilibrium. The real universe consistently outperforms fiction in terms of scale and complexity. And despite centuries of observation, humanity still understands only a fraction of it. There are likely stranger stars than R136a1 waiting to be discovered. Larger black holes, more violent explosions, new physical phenomena operating in environments humans have not yet observed clearly. Every generation of astronomy expands the known universe and simultaneously reveals how much remains unexplored. That uncertainty is not frustrating. It is wonderful. The cosmos still contains mysteries. Somewhere across the observable universe, giant stars are forming right now inside dense glowing nebulae. Others are collapsing. Some may already have exploded while their light continues travelling silently through space toward future civilizations not yet born. And perhaps, somewhere, under conditions more extreme than those inside the Tarantula Nebula, even larger stars exist briefly before gravity and radiation tear them apart. Nature appears surprisingly comfortable, experimenting with impossible things. Still, there is one final thought worth lingering on before tonight's journey drifts to a close. R136a1 feels extraordinary, partly because human beings naturally think in terms of permanence. We admire things that endure: mountains, oceans, ancient forests, civilizations lasting centuries. Giant stars challenge that instinct. The universe sometimes creates objects of astonishing power and scale that survive only briefly. Brilliance does not guarantee longevity. In fact, in stellar physics, brilliance often shortens it. Small stars live quietly for trillions of years. Giant stars burn themselves apart quickly. There is something deeply honest about that trade-off. R136a1 spends energy recklessly. It pours radiation into surrounding space continuously while dismantling itself through stellar winds. The star's future collapse is inevitable from the moment it forms, yet during its brief existence it transforms its environment profoundly. Perhaps the universe builds monsters like R136a1 because transformation itself requires intensity sometimes. Heavy elements require fusion. Fusion requires pressure. Pressure requires gravity. And under the right conditions, gravity occasionally creates stars so enormous that even nature struggles to keep them stable for long. The result is temporary magnificence. A short-lived giant illuminating surrounding darkness before collapse eventually claims it. And somehow, from processes like these, galaxies evolve, planets form, life emerges, consciousness appears, a species develops telescopes, and eventually someone lies awake at night listening to the story of a star possibly far away, while the quiet, ordinary world continues around them. That connection between the immense and the intimate may be the most remarkable thing astronomy offers us. The universe is vast beyond comprehension, yet somehow, after billions of years of stellar evolution and cosmic history, a tiny part of that universe became capable of wondering about itself. And tonight, one of those wonders is a giant unstable star called R136a1, still blazing furiously in the darkness, still balancing against collapse, still reminding us that nature occasionally builds things not because they last forever, but because for a brief moment they can burn brighter than almost anything else in existence.